There's a rule. It's not just a good idea, it's the law. It's a law woven into the very fabric of reality, a cosmic speed limit that nothing is ever supposed to break. That limit is the speed of light. It's the fastest anything can travel, anywhere, period. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if I told you that as you're watching this, entire galaxies are absolutely shattering that speed limit? That huge chunks of the cosmos are flying away from us faster than light itself? This isn't some sci-fi concept. It's a documented, observed fact of our universe. It's a story about how space itself found a loophole in its own rules. A story about a mysterious force pushing everything apart, and a growing suspicion that this force isn't at all what we thought it was. This is the story of how we are actively losing pieces of our universe forever as they speed past a point of no return. And, in a twist that's challenging everything we thought we knew, we're now getting hints that the universe might have just slammed on the brakes. The unbreakable rule. Einstein's cosmic speed limit. To get how the universe breaks its own speed limit, we first have to understand the limit itself. And for that, we need to go back to the early 20th century, to a young patent clerk in Bern, Switzerland, named Albert Einstein. In 1905, Einstein dropped his theory of special relativity, and with it, he laid down the law. He wasn't just describing how things move. He was describing the actual structure of space and time. At the heart of it was a wild idea. The speed of light in a vacuum, c, is absolute. It doesn't matter if you're standing still or zipping through space in a rocket. If you turn on a flashlight, that beam will race away from you at the exact same speed. Roughly 299,792 kilometers per second. This had some huge consequences. One of them is the most famous equation in science. E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are just two sides of the same coin. It also tells us why nothing with mass can ever hit the speed of light. Think of it this way. As you speed up, your kinetic energy increases. According to Einstein, that energy has to go somewhere, and it goes into increasing your relativistic mass. You get heavier the faster you go. As you get closer and closer to the speed of light, your mass approaches infinity. Pushing an infinitely massive object would take an infinite amount of energy, and since there isn't an infinite amount of energy to spare, the speed of light becomes a wall you can't break through. It's the ultimate cosmic speed limit. And this isn't just a theory, it's one of the most rigorously tested ideas in all of physics. Particle accelerators like the Large Hadron Collider push tiny particles to 999,999% of light speed every single day, and every single time, Einstein is right. The particles get unbelievably energetic, but they never, ever cross that barrier. This limit is also what holds causality together, the idea of cause and effect. If you could go faster than light, you could theoretically arrive somewhere before you left. You could get a message before it was sent. The universe would spiral into paradox and chaos. So, the speed of light isn't just a limit, it's a guardrail for reality itself. For over a century, we thought it was an unbreakable rule. And in a way, it is. But the universe, it turns out, is a lot more clever than we gave it credit for. The Great Escape, Hubble and the expanding universe. For most of human history, we saw the universe as a static, unchanging stage. The stars were just fixed points of light in a great, dark theater. That was the view, even for Einstein. He, like pretty much everyone, assumed the universe, on the whole, was holding still. But then, in the 1910s and 20s, an astronomer named Vesto Slipher started noticing something weird at the Lowell Observatory in Arizona. He was studying the light from what they called spiral nebulae, fuzzy blobs we now know are entire galaxies. When he passed their light through a prism, spreading it into a spectrum, he saw that the familiar patterns of elements were shifted. For almost all of them, the lines were shifted towards the red end of the spectrum. This is the famous phenomenon of redshift. It's the cosmic version of the Doppler effect. Just like the pitch of an ambulance siren drops as it speeds away from you, the wavelength of light from something moving away gets stretched, making it look redder. What Slipher had discovered was that nearly every galaxy he looked at was moving away from us, some at incredible speeds. The next piece of the puzzle came from Henrietta Swan Leavitt, an astronomer at the Harvard College Observatory. She was studying a type of star called a Cepheid variable, which pulses in brightness on a regular schedule. Leavitt found something crucial. The longer the star's pulse, the greater its true brightness. This was a game changer. Cepheid variables could be used as standard candles. By timing their pulses, you knew how bright they really were. And by comparing that to how dim they looked from Earth, you could calculate their distance. It was Edwin Hubble who put it all together. Using the brand new 100-inch Hooker telescope in California, Hubble spotted these Cepheid variables in distant nebulae. His calculations proved, once and for all, that these weren't just gas clouds in the Milky Way. They were massive, faraway, island universes, galaxies just like ours, millions of light years away. Then, Hubble combined his distance measurements with Slipher's redshift data. What he found was a bombshell. The farther away a galaxy was, the faster it was moving away from us. This wasn't random. It was a clear relationship, a law that now carries his name. Hubble's law. The conclusion was inescapable and it shattered the old paradigm. The universe wasn't static. It was expanding. To picture this, think of a loaf of raisin bread dough rising in an oven. Pick any raisin, that's us. As the dough expands, all the other raisins move away. A nearby raisin moves away slowly. A raisin on the far side of the loaf moves away much, much faster. The key is this. The raisins aren't moving through the dough. They're being carried along by the expansion of the dough itself. And that's the secret to our cosmic paradox. Galaxies aren't like rockets blasting through space. For the most part, they're just sitting in their own local neighborhood. It's the fabric of spacetime itself that's stretching, creating more distance between everything. A galaxy 26 million light-years away recedes at a certain speed. A galaxy twice as far recedes at twice that speed. And if you look far enough away, the combined stretch of all that space adds up to a speed faster than light. This doesn't break Einstein's rule. No galaxy is moving through its local patch of space faster than light. No information is being sent from A to B faster than light. The local speed limit is still in effect. But the global expansion of space itself? It has no speed limit. It's the universe's brilliant loophole. For decades, this was our mind-bending picture of the cosmos. But the story was about to get even weirder. The standard story. A universe on runaway. Once Hubble proved the universe was expanding, the next big question was, what's its ultimate fate? The expansion was kicked off by the Big Bang, but it was in a constant tug-of-war with the gravity of all the matter in the universe pulling everything back together. For most of the 20th century, there were two main ideas. If there was enough stuff and enough gravity, the expansion would slow, stop, and reverse into a big crunch. If there wasn't enough matter, gravity would lose, and the universe would expand forever, getting slower and slower, fading into a big freeze. To figure it out, astronomers needed to measure how much the expansion was slowing down. In the late 1990s, two separate teams set out to do just that, using an even better standard candle, Type Ia supernovae. A Type Ia supernova is a spectacular explosion that happens when a dead star called a white dwarf steals material from a companion star. Once the white dwarf hits a critical mass about 1.4 times the mass of our Sun, it triggers a thermonuclear explosion so bright it can outshine its entire galaxy. Because they all blow up at the exact same mass, they all have almost the exact same peak brightness. They are fantastic standard candles, visible across billions of light years. The two teams hunted for these distant explosions to map the universe's expansion history. But when they got the data back, it showed something that seemed impossible. The most distant supernovae were dimmer and therefore farther away than they should have been in any universe that was slowing down. The only explanation was that the expansion wasn't slowing down at all. It was speeding up. The universe wasn't just expanding, it was accelerating. This discovery, published in 1998, was so revolutionary it won the Nobel Prize in 2011. It meant the universe wasn't headed for a big crunch or a slow fade. It was a runaway train, being pushed apart by some mysterious, anti-gravity force. Scientists gave this force a name: dark energy. This led to our standard model of cosmology, called the lambda cold dark matter model, or lambda CDM. The lambda is dark energy, imagined as a cosmological constant, an idea Einstein himself came up with and then famously called his biggest blunder. In this view, dark energy is just a property of space itself. Every cubic meter of empty space has a tiny, but constant, amount of this repulsive energy. As space expands, more space is created, and with it, more dark energy, pushing the expansion even faster. For over 2 decades, this has been our official story of the cosmos. But science is never really settled. And deep inside the data, a crack was starting to show. The Hubble tension. The first crack in the foundation. As our measurements got better, a stubborn problem popped up. It's known as the Hubble tension, and it's one of the biggest crises in modern cosmology. Here's the issue. We have 2 completely different ways to measure how fast the universe is expanding today, the Hubble constant, and they don't agree. The first method looks at the late universe, the cosmos relatively nearby. Astronomers use standard candles like Cepheid variables and Type Ia supernovae to build a cosmic distance ladder and calculate the current expansion rate. This method consistently gives a value of around 73 to 74 kilometers per second per megaparsec. The second method looks at the early universe. It uses the afterglow of the Big Bang, the cosmic microwave background, CMB, which is the light from when the universe was just 380,000 years old. Satellites like Planck have mapped this light in incredible detail. By plugging the patterns in the CMB into our standard lambda CDM model, scientists can predict what the Hubble constant should be today. This early universe method consistently gives a value of around 67 kilometers per second per megaparsec. The gap between 67 and 73 might not sound like a lot, but with the precision of these measurements, it's a chasm. The error bars don't overlap. It suggests that either our measurements are wrong, or the lambda CDM model itself, our fundamental understanding of the universe, is missing something important. Scientists have been racing to find an independent way to measure the constant and break the tie. And now they have one. Gravitational waves. When massive objects like black holes collide, they send out ripples in spacetime. The detection of these waves from a neutron star merger in 2017 gave us the first standard siren measurement. And very recently, in early 2026, a new stochastic siren technique was developed. Instead of one bright event, it uses the faint background hum from countless black hole mergers all over the cosmos. So far, these gravitational wave methods seem to lean toward the higher, late universe value, only deepening the mystery. The cracks in our standard model were getting wider. And then, another bombshell dropped. The 2026 bombshell. Did the universe hit the brakes? For nearly 30 years, the idea of an accelerating universe has been the bedrock of cosmology. But what if that whole story is wrong? In late 2025 and early 2026, a series of studies began sending shockwaves through the scientific community. One of the most significant, led by Professor Young-Wook Lee of Yonsei University, took a hard look at the very type Ia supernovae that started it all. The original discovery assumed these explosions were perfect standard candles. But the new study argued this was a flawed assumption. They presented evidence that the brightness of a supernova is affected by the age of the galaxy it's in. Supernovae in younger galaxies seem to be a bit fainter than those in older ones. It's a subtle correction, but with profound consequences. When Lee's team applied this age bias correction to the data, the picture flipped. The evidence for acceleration seemed to vanish. In fact, their results suggested the opposite. According to their analysis, the universe may no longer be accelerating. It might have already started to slow down. As Professor Lee put it, our study shows that the universe has already entered a phase of decelerated expansion. If these results are confirmed, it would mark a major paradigm shift in cosmology since the discovery of dark energy 27 years ago. This isn't happening in a vacuum. Other evidence has been pointing to something strange. The Dark Energy Spectroscopic Instrument, DESI, has been building the largest 3D map of the universe, and its recent data also shows hints that dark energy might not be constant but could be evolving and weakening over time. While the DESI team suggests deceleration could happen in the future, Lee's corrected data argues it's happening now. This could change everything. If dark energy isn't a constant, then lambda CDM, our standard model, is at best incomplete. Dark energy isn't a static feature of space, but a dynamic force that's fading away. This could even be the key to solving the Hubble tension, potentially reconciling the different measurements from the early and late universe. We thought we were on a runaway roller coaster, but it's possible the operator just pulled the emergency brake. Faster than light and the unreachable universe. So, what does this mean for our original paradox? If the universe is slowing down, are galaxies no longer breaking the light-speed barrier? The answer, surprisingly, is no. The phenomenon of faster-than-light recession is still very much a thing. Think back to the raisin bread. Even if the dough is rising more slowly now than it was a minute ago, it's still expanding. The distance between the raisins is still growing. It's the cumulative effect over huge distances that counts. There's a point, called the Hubble sphere, about 14 billion light-years away, where the expansion speed equals the speed of light. Any galaxy beyond that point is currently receding from us faster than light. A galaxy at the edge of our observable universe, about 46 billion light-years away in proper distance, is moving away from us at more than 3 times the speed of light. That's true whether the expansion is speeding up or slowing down. The sheer amount of expanding space between us and them guarantees it. What does change is our ultimate fate and what we can see. In the old, accelerating model, we are surrounded by a cosmic event horizon. As the expansion speeds up, galaxies are pushed past this point of no return. Once they cross it, any light they emit can never reach us. They are cut off from us forever. In that scenario, we would see fewer and fewer galaxies over time as they wink out, one by one. We'd be doomed to an increasingly lonely existence. But a decelerating universe completely rewrites that ending. If the expansion is slowing, gravity is starting to win back some ground. The event horizon could disappear. Light from distant galaxies now has a fighting chance. Light that was being swept away by expansion can now start making headway toward us. This means that, in theory, we might one day see galaxies that are currently invisible to us. The number of galaxies we can see could actually grow over cosmic time. Instead of an emptier and emptier sky, we could be heading towards a future with an even richer one. Of course, if the deceleration is strong enough and dark energy keeps weakening, it might even bring back the possibility of that Big Crunch, theorized a century ago, where the universe collapses back in on itself. These new findings have reopened that as a physical possibility. We are living through a revolution in how we see the cosmos. The rules we thought we knew are being challenged, and the fate of everything is once again an open question. If this journey has expanded your universe, make sure to subscribe and hit the bell. We're at a huge turning point in cosmology, and you won't want to miss what we find next. We started with a paradox. How can galaxies move faster than light without breaking the laws of physics? The answer, we found, is in the stretching of spacetime itself, which carries galaxies along for a ride so vast that the cumulative speed breaks the ultimate limit. We walked through the story we thought we knew. A universe running away with itself, pushed by a constant, mysterious dark energy. But then we found the cracks in that story, a deep tension in our measurements and, just recently, tantalizing evidence that the acceleration may have already stopped. We might be in a decelerating universe after all. This doesn't stop distant galaxies from receding faster than light, but it could radically change our future. Instead of being doomed to a lonely cosmos as galaxies disappear, we might live in one where lost regions could one day swim back into view. What is dark energy? Is it a constant, or a dynamic field that's fading away? Will the universe expand forever, or is it destined for collapse? The truth is, right now, we don't know. The latest discoveries haven't given us a final answer, but they have blown the doors wide open. The standard model of cosmology, our guide for a generation, is facing its greatest challenge yet. And that is the most beautiful thing about science. It's not a set of facts carved in stone, but a living, evolving story. A story that is constantly being tested and rewritten. We are explorers mapping a cosmic ocean, and we've just found out our charts might be wrong. A new, more mysterious, and far more interesting universe is waiting to be discovered. The only thing we know for sure is that the journey is far from over. Space isn't empty, it's stretching. We tend to think of space as a vast, empty container. A black, silent room we're all just flying through. It's the background. The stage. The ultimate void separating the points of light we call stars and galaxies. For most of human history, this wasn't just a feeling, it was the accepted truth. Space was the fixed, unchanging arena where the drama of the cosmos played out. But that's not the whole story. In fact, it's not even the most interesting part. The biggest secret of the universe isn't what's in space. It's what space itself is doing. Because space isn't empty. It's stretching. And it's taking all of us for a ride. This single idea that the very fabric of reality is dynamic and expanding is one of the most profound and counterintuitive discoveries in the history of science. It dismantles everything we think we know about movement, distance, and our place in the cosmos. It forces us to abandon the comfortable idea of the universe as a static room and embrace a far stranger, more active reality. Today, we're going to dismantle that grand illusion. We'll explore how we discovered this cosmic stretch, what it actually means for space to expand, and how this revelation leads to mind-bending consequences that seem to break the laws of physics, but really, reveal their true nature. You're about to see the universe not as an empty void, but as a living, growing entity. The grand illusion of an empty room. Our minds are wired for life on Earth. We walk through rooms, drive down highways, and see birds fly across the sky. In every single one of these experiences, there's a clear distinction. There are the asterisk objects that move, and there is the asterisk space they move through. The space itself is passive. The walls of your room aren't actively pushing you away from your screen. The air isn't expanding to make the journey to the kitchen longer. To our senses, space is a static, absolute, and empty stage. This intuition is so powerful that it was baked into the very foundations of classical physics. For centuries, the dominant scientific view was that of Sir Isaac Newton. A universe operating inside an infinite, rigid framework of space and time. Space was a three-dimensional grid, an unmoving cosmic graph paper where the stars and planets were placed. It was the ultimate reference frame, the motionless backdrop against which all true motion could be measured. This empty room model of the universe just feels like common sense. And for a long time, this model worked perfectly. It let us predict the orbits of planets, the paths of cannonballs, and the tides of the oceans. But as the 19th century gave way to the 20th, our tools for looking at the cosmos grew far more powerful. Telescopes got bigger, photography became more sensitive, and a new technique called spectroscopy allowed astronomers to do something incredible. Analyze the light from distant objects, breaking it down into a rainbow to decipher not just their chemical makeup, but crucially, their motion. As we looked deeper, cracks began to appear in the elegant, static facade of Newton's universe. The first tremor came from a debate about a class of objects known as spiral nebulae. These were faint, fuzzy swirls of light scattered across the sky. For decades, astronomers argued over what they were. Were they baby solar systems, clouds of gas condensing within our own Milky Way? Or were they, as some audaciously proposed, entire island universes? Vast, distant galaxies just like our own, separated from us by unimaginable gulfs of empty space? This argument, which peaked in the Great Debate of 1920, was about more than just classifying celestial objects. It was a debate about the scale of reality itself. If these nebulae were inside our galaxy, the universe was a relatively cozy place. But if they were other galaxies, then the universe was incomprehensibly vast, and our own galaxy was just one of countless others. The answer would ultimately shatter the empty room illusion. Because once we understood the true distances to these island universes, we were forced to confront an even more shocking reality. Not only were they far away, but they were all running away from us. The static, comfortable room of the Newtonian cosmos was about to be demolished, revealing a universe that was far more dynamic and far stranger than anyone had ever imagined. The clues were hidden in the light, waiting for the right minds to piece them together. The whispers of a stretching cosmos. The story of how we discovered the expanding universe is a tale of brilliant minds, overlooked genius, and a revolution that happened almost by accident. It didn't start with a big declaration, but with the quiet, meticulous work of an astronomer often forgotten by history. Vesto Slipher. Working at the Lowell Observatory in Arizona back in the 1910s, Slipher took on a laborious project, systematically measuring the spectra of those faint spiral nebulae. He wasn't trying to discover the fate of the universe. Using spectroscopy, he could see if the light from these objects was shifted. A shift toward the blue end of the spectrum, a blue shift, meant an object was moving toward us. A shift toward the red end, a redshift, meant it was moving away. This is the Doppler effect, the same reason a siren's pitch changes as it passes you. Slipher probably expected to find a random mix of redshifts and blue shifts, some nebulae approaching, some receding, just as you'd expect from objects moving around in a static space. And sure enough, the first one he measured, the Andromeda Nebula, showed a blue shift, meaning it was heading toward us. But as he kept working, night after night, a stunning and inexplicable pattern emerged. Of the dozens of nebulae he measured, the vast majority were redshifted. And not just slightly. They were flying away from us at astonishing speeds, some over 1,000,000 miles an hour. This was a profound mystery. By 1917, Slipher had presented his findings, but nobody really knew what to make of it. The idea that these were distant galaxies wasn't yet confirmed, and the static universe was still the default. Slipher had found the key piece of evidence for cosmic expansion, but the theory was missing. That theory arrived, not from an observatory, but from the mind of a Belgian Catholic priest and physicist named Georges Lemaitre. In the 1920s, Lemaitre was one of the few people exploring the radical implications of Albert Einstein's new theory of general relativity. Einstein's equations described how matter and energy warp spacetime to create gravity. But when Einstein applied his own equations to the universe as a whole, he was horrified. They predicted that the universe couldn't be static, it had to be either expanding or contracting. This bothered Einstein so much that he added a cosmological constant to his equations, a fudge factor to hold the universe still, something he later called his biggest blunder. Lemaitre, however, took the equations at face value. In 1927, he published a paper in a little-known Belgian journal that described an expanding universe. More than that, he did what no one else had. He connected the theory to the observations. He proposed that the redshifts measured by Vesto Slipher were the direct evidence of this cosmic expansion. He even used the available data to calculate the expansion rate, a value we now call the Hubble constant. Lemaitre had, in essence, discovered the expanding universe. But his work was published in French and largely ignored. The final blow to the static universe came from the man whose name would, for a time, overshadow Lemaitre's, American astronomer Edwin Hubble. Working at the magnificent Mount Wilson Observatory, Hubble had the world's most powerful telescope. In 1924, he used it to spot a special type of pulsating star inside the Andromeda Nebula. Because the true brightness of these stars was known, he could calculate their actual distance. His result was staggering. Andromeda was nearly 1 million light-years away, far outside the Milky Way. It was, definitively, an island universe. This discovery blew the lid off our conception of the cosmos. Now knowing the universe was filled with countless galaxies, Hubble and his assistant Milton Humason systematically measured their distances and their redshifts. In 1929, Hubble published a paper that changed history. He presented a simple graph plotting a galaxy's distance against its speed. The result was a clear, undeniable straight line. The farther away a galaxy was, the faster it was moving away from us. This elegant relationship became known as Hubble's law. It was the definitive proof that the universe was expanding. The whispers first detected by Slipher, and the theory first articulated by Lemaitre, were now shouted to the world. The static room of Newton's universe was gone forever. But this raised a new, even more perplexing question. If everything is moving away from us, does that make us the center of the universe? The answer would require a complete shift in how we think about space itself. The rising dough universe, the core analogy. So, if all the distant galaxies are receding from us, that must mean we're at the center of a colossal cosmic explosion, right? It's a natural conclusion. And it's completely wrong. This is where our intuition, shaped by a static world, fails us spectacularly. The universe has no center. And the galaxies are not actually flying through space at all. To get this, we need a new mental model. Let's throw out the empty room and replace it with something you can picture in your kitchen. A loaf of raisin bread dough, rising in the oven. Imagine the loaf of dough as the entire universe, extending infinitely in all directions. And scattered throughout this dough are raisins, which represent galaxies. Now, as the dough bakes, it expands uniformly, everywhere. Let's pick a single raisin, our home raisin. From its perspective, what do we see? A nearby raisin, say 1 inch away, moves to 2 inches away as the dough doubles in size. It has moved 1 inch from us. But now look at a raisin that was originally 5 inches away. When the dough doubles, it's now 10 inches away. It has moved 5 inches from us in the same amount of time. It appears to be moving 5 times faster. This simple analogy perfectly explains Hubble's law. The farther away a galaxy is, the faster it appears to be receding. It's not because it has a more powerful engine, but simply because there's more expanding, more space between it and us. Now, what about the center? If we hopped over to that other raisin, we'd see the exact same thing. Our home raisin would look like it's speeding away. From the perspective of any raisin, all the other raisins are moving away. In an infinitely expanding loaf of raisin bread, every single raisin can claim to be the center. And if everyone is at the center, then nobody is. This brings us to the most critical point. The raisins aren't moving through the dough. They're just sitting there, at rest in their little patch of dough. It's the dough itself, the very fabric of space, that is expanding and carrying the raisins along for the ride. This is the difference between a galaxy's own peculiar motion and the Hubble flow. Peculiar motion is a galaxy's individual movement through its local patch of space, caused by the gravitational pull of its neighbors. This is why the Andromeda galaxy is actually moving towards us. Our local gravitational attraction is strong enough to overcome the cosmic expansion on this small scale. But the Hubble flow is the motion of being carried along by the expansion of the universe itself. For distant galaxies, this expansion dominates. They're like the raisins in our loaf, passively carried apart as the space between them stretches. This isn't a force pushing them. It's just a fundamental property of spacetime. This also helps us with another baffling question. What is the universe expanding into? We picture the loaf expanding into the oven. But in our analogy, the dough is the entire universe. There is no oven. There is no outside. Asking what space is expanding into assumes space is a thing inside something else. But general relativity teaches us that space is a self-contained thing whose geometry can change. It doesn't need to expand into anything, it just expands. The realization that space is an active, stretching fabric is the key that unlocks cosmology. It changes everything and leads to consequences so bizarre they seem to defy the laws of physics. The mind-bending consequences. The moment you truly accept that space itself is stretching, the universe gets weird. And I mean, really weird. This single idea reframes everything we see and leads to some genuinely mind-bending outcomes. Let's start with redshift. We first think of it as a Doppler effect, like a siren. But the redshift from distant galaxies is something more fundamental, called cosmological redshift. Imagine a photon of light is emitted from a distant galaxy. This photon is a tiny wave traveling through space. But while it's in transit, the space it's traveling through is stretching. The light wave itself, being a ripple in spacetime, gets stretched along with it. By the time that photon reaches our telescopes billions of years later, its wavelength has been physically elongated. It might have been emitted as blue light, but it arrives as red or even infrared light. The amount of redshift is a direct measure of how much the universe has stretched since that light began its journey. This leads us to the most startling consequence. Galaxies that are receding from us faster than the speed of light. Wait, what? We all learn Einstein's ultimate speed limit. Nothing can travel through space faster than the speed of light. This is a sacred rule of physics. So how can this be possible? The key is that phrase, through space. The cosmic speed limit applies to an object's motion relative to the space in its immediate vicinity. But there is no known law that limits the speed at which space itself can expand. The Hubble flow isn't motion through space, so it's not bound by the speed of light. The rate of expansion, the Hubble constant, is about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means for every 3.26 million light-years you look farther out, the universe is expanding an additional 70 kilometers per second faster. If you do the math, you find that at a distance of about 14.4 billion light-years, this cumulative expansion speed breaks the speed of light. This boundary is called the Hubble sphere. Any galaxy beyond this is receding from us faster than light, purely because of all the space stretching between us and it. Let that sink in. There are trillions of galaxies out there whose light, if emitted today, would never reach us. They are being carried away by the river of expanding space faster than they can swim upstream toward us at light speed. They have crossed a cosmic point of no return. We can still see the ancient light they emitted billions of years ago when they were closer, but their present and future are forever beyond our reach. In a very real sense, the expansion of space is causing our observable universe to shrink, as more and more galaxies cross this cosmic event horizon. This concept also explains the true scale of the universe. The universe is 13.8 billion years old. Naively, you'd think the farthest we could see is 13.8 billion light-years away. But because space has been expanding that whole time, an object whose light traveled for 13.8 billion years to reach us is now actually much farther away. The current distance to the edge of the observable universe is about 46 billion light-years. The light from those most distant galaxies was emitted when they were much closer, but even then, many were already receding from us faster than light. We can only see them because the expansion was slower in the past, allowing the light to make some headway. The stretching of space isn't just a quirky feature, it's the operating system of the cosmos. It dictates what we can see, what we can ever hope to see, and redefines the very concepts of distance and motion. But the story doesn't end there. The expansion itself holds one more giant mystery. The deeper mystery. So, space is stretching. This carries galaxies apart, making the most distant ones recede faster than light. But this all leads to one ultimate question. Why? What's driving the expansion? For decades, cosmologists assumed the expansion must be slowing down. After all, the universe is filled with matter, and gravity pulls things together. Like a ball thrown in the air, the initial push from the Big Bang should be constantly fighting against the gravitational pull of everything. The expansion should be getting slower and slower. Then, in 1998, two separate teams of astronomers made a discovery so shocking it won them the Nobel Prize. By using a specific type of supernova to measure cosmic distances with stunning accuracy, they found the expansion of the universe is not slowing down. It's speeding up. This acceleration kicked in about 5 to 6 billion years ago. Something is not just counteracting gravity. It's overwhelming it on the largest scales, pushing everything apart at an ever-increasing rate. We have a name for this mysterious something: dark energy. The dark in dark energy is just a beautiful way of saying we have no idea what it is. It seems to be a property of space itself, an intrinsic energy of the vacuum that makes up an estimated 68% of the universe. As space expands, more space is created, and with it, more of this repulsive dark energy. This creates a runaway feedback loop that pushes the universe apart faster and faster. And to make things even more complicated, a crisis has emerged in cosmology known as the Hubble tension. When we measure the expansion rate today using nearby objects like supernovae, we get a value of about 73 kilometers per second, (mpc). But when we use our best model of the early universe and the light from the Big Bang's afterglow to predict what the rate should be today, we get a different value, about 67 kilometers per second, (mpc). This discrepancy is too big to ignore. It means either our measurements are wrong, or, more excitingly, our standard model of cosmology is missing something fundamental. Perhaps dark energy is changing over time. New methods, like using the faint background hum of gravitational waves, are being developed to provide a completely independent measurement and hopefully solve this tension. The story of our universe is still being written, and mysteries like dark energy and the Hubble tension are the next chapters. If you want to dive deeper into the crisis in cosmology and what might be causing the universe to fly apart, that's exactly where we're going next. We started with a simple idea. Space is an empty room. A void. But as we've journeyed from the first hints of redshift to the mind-bending reality of a stretching cosmos, that room has dissolved. In its place is a dynamic fabric, an entity whose own growth dictates the fate of the trillions of galaxies woven into it. The light that reaches us from the distant universe isn't just a postcard from a faraway place. It's a message from a different time, its wavelength physically stretched by the expansion of space itself. The galaxies we see are not just fleeing from us, they are passengers on a cosmic current. And the most distant of them have already been swept over a cosmic horizon, their futures forever cut off from our own. The next time you look up at the night sky, don't just see a static collection of stars. See the fabric of reality itself, alive and in motion. You're not just looking out into space. You're looking back in time across a universe that has stretched and grown to bring that ancient light to you. We aren't just living in the universe. We are part of its expansion. We are all, right now, riding on the skin of a stretching cosmos. Einstein's one law the entire universe ignores. In the universe, there are rules. Unbreakable laws that dictate how stars burn and how light travels across cosmic voids. But one rule stands out, a cosmic speed limit that's the foundation of our reality. Albert Einstein figured it out, and it's beautifully simple. Nothing can travel faster than the speed of light. This isn't just a guideline, it's the bedrock of modern physics. It ensures that cause comes before effect, it keeps the door to time travel locked, and it defines the relationship between matter and energy. It's the most solid, absolute limit we know. But what if I told you the universe itself doesn't seem to care? What if, right now, huge patches of the cosmos are blowing right past that ultimate speed limit? Across the mind-bending emptiness of space, entire galaxies are flying away from us faster than light. How is that possible? Are the laws of physics broken? The answer is a dive into a cosmic paradox, a story of how the fabric of reality itself can stretch and expand in ways that twist our common sense into knots. This is the story of how the universe gets away with breaking Einstein's one unbreakable law. The unbreakable law, forging the cosmic speed limit. To really feel how big this cosmic rebellion is, we first have to understand the law it seems to be breaking. This isn't just a rule somebody dreamed up, it's a conclusion baked into the math of our universe. Our story starts not in deep space, but in the mind of a young Albert Einstein around the start of the 20th century. Back then, physicists were stuck on a puzzle. Isaac Newton's laws of motion were perfect for everything from a falling apple to the moon's orbit. But a new set of laws from James Clerk Maxwell described the bizarre world of electricity, magnetism, and light. The problem? The two sets of laws didn't play nice. Maxwell's equations predicted something wild. The speed of light in a vacuum is constant. It doesn't matter if you're standing still, racing toward a light beam, or running away from it. If you measure its speed, you always get the same number. Exactly 299,792, 458 meters per second. This was just weird. Think about it. You're on the highway doing 60, and a car passes you doing 70. From your point of view, it's only pulling away at 10 miles per hour. That's just common sense. But light doesn't work that way. If you could travel at half the speed of light and turn on a flashlight, you wouldn't see the light beam moving away at half the speed of light. You'd measure it moving away at the asterisk full speed of light. Every time. Einstein didn't shy away from this contradiction, he leaned into it. He made the bold assumption that Maxwell was right, the speed of light is absolute. From that one idea, he built his theory of special relativity, and in the process, completely rewrote our understanding of space and time. The consequences were mind-blowing. He showed that space and time aren't separate things, but are woven together into a single, four-dimensional fabric called spacetime. And one of the biggest results of this theory is the cosmic speed limit. So why is this limit so solid? The reason is hidden in one of the most famous equations ever, E equals mc squared. This equation shows that mass and energy are two sides of the same coin. A more complete version of the math includes something called the Lorentz factor. It looks complex, but the idea is simple. The faster something with mass moves, the more its effective mass, its resistance to being pushed, goes up. Imagine you're trying to push a car. At first, it's tough but doable. Now, imagine that for every bit of speed you add, the car gets heavier. As you get closer and closer to the speed of light, the car's mass starts to skyrocket, heading towards infinity. To push an infinitely massive object any faster would take an infinite amount of energy. Since there isn't an infinite amount of energy to go around, it's physically impossible for anything with mass to ever hit the speed of light. It's the ultimate barrier, hard-coded into the universe's operating system. This isn't just a theory. It's something scientists see every day at places like the Large Hadron Collider. They pump incredible amounts of energy into tiny particles to get them to 999,999% of light speed, and they can directly measure this increase in effective mass. The theory works. This speed limit also acts as the universe's traffic cop for cause and effect. It ensures that an effect can't happen before its cause. If you could send a message faster than light, you could get a reply before you even sent the question, creating paradoxes that would tear the logical fabric of reality apart. So, Einstein's law is more than just a speed limit, it's the glue holding our logical universe together. It's a perfect, elegant, and supposedly absolute law. The first cracks in reality, a universe in motion. For most of history, we pictured the universe as a calm, still, and eternal stage. This was Newton's universe, and even Einstein believed it at first. In fact, when his own equations for general relativity, his theory of gravity, suggested the universe should be growing or shrinking, he hated the idea so much that he stuck in a fudge factor to force the universe to hold still. He later called it his biggest blunder. The universe, as it turned out, had other ideas. The first clues that the cosmos was more dynamic came from patient astronomers. In the 1910s, an astronomer named Vesto Slipher was studying faint, blurry spirals in the sky called spiral nebulae. Using a technique called spectroscopy, which splits light into its rainbow of colors, he found something startling. When an object moves away from you, its light waves get stretched out, shifting them toward the red end of the spectrum. This is called redshift. If an object moves toward you, its light is compressed, shifting it toward the blue end, a blue shift. Slipher looked at the light from these spiral nebulae and saw that almost all of them were massively redshifted. Not only that, but some were receding at incredible speeds, way faster than anything in our own Milky Way. These nebulae were running away from us. But what were they? And why were they in such a hurry? The mystery was solved thanks to two other pioneers, Henrietta Swan Leavitt and Edwin Hubble. Henrietta Swan Leavitt, working at Harvard, studied a special kind of star called a Cepheid variable. These stars pulse, getting brighter and dimmer with a precise rhythm. In 1912, Leavitt found the key. The longer it takes a Cepheid to pulse, the brighter it truly is. This was a game changer. It meant these stars could be used as standard candles. If you know how bright a light bulb really is, you can tell how far away it is by how dim it looks. Leavitt had just handed astronomers a cosmic measuring tape. Enter Edwin Hubble. In the 1920s, using the most powerful telescope on Earth at the Mount Wilson Observatory, Hubble pointed it at the Andromeda Nebula. He found Cepheid variable stars inside it. Using Leavitt's method, he calculated the distance to Andromeda and got a shocking result. Nearly 1 million light-years. This was way outside the known boundaries of the Milky Way. That single measurement changed our entire view of the universe. Those spiral nebulae weren't clouds inside our galaxy. They were entire galaxies themselves, vast, island universes, separated by oceans of empty space. The known universe had just gotten unbelievably bigger. But Hubble didn't stop there. He took his distance measurements and combined them with Vesto Slipher's redshift data. He plotted dozens of galaxies on a chart, their distance from us on one axis, and the speed they were moving away on the other. What he found in 1929 was a simple, powerful pattern that became the bedrock of modern cosmology. The farther away a galaxy was, the faster it was moving away from us. A galaxy twice as far away was receding twice as fast. A galaxy 10 times farther away was receding 10 times as fast. This clean, straight-line relationship became known as Hubble's law. It's often written as a simple equation: velocity equals h0 times distance. That h0 is the famous Hubble constant, a number representing the universe's expansion rate. The conclusion was unavoidable. The universe wasn't static. The space between galaxies was growing. The entire fabric of the cosmos was stretching. We live in an expanding universe. And this discovery, born from the patient work of stargazers, was about to set up a direct collision with Einstein's most sacred law. The paradox deepens. When running becomes faster than light. Hubble's discovery was a triumph. It proved the universe was a dynamic, evolving place. But hidden inside his simple equation was a ticking time bomb, a logical conclusion so bizarre it seemed to threaten physics itself. Let's look at Hubble's law again. Velocity equals h0 times distance. It says a galaxy's speed is directly tied to its distance. This means there's no cap on the potential speed. If you look far enough out, the velocity calculated by this equation will eventually get bigger than any number you can think of, including the speed of light. Let's do some quick math. The modern value for the Hubble constant is around 70 kilometers per second per megaparsec. A megaparsec is just a huge unit of distance astronomers use, equal to about 3.26 million light-years. So, for every 3.26 million light-years you go out into space, the universe is expanding 70 kilometers per second faster. A galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 km per second. Now, the speed of light is roughly 300,000 km per second. At what distance does a galaxy's recession speed break that ultimate limit? We can figure it out. If we divide the speed of light, 300,000 km per second, by the Hubble constant, 70 km per second, MPC, we get a distance of about 4,285 megaparsecs. That's around 14 billion light-years. This boundary is called the Hubble sphere. Any galaxy beyond this point, according to Hubble's law, must be receding from us faster than the speed of light. Let that sink in for a moment. Einstein, with special relativity, put up a cosmic signpost that said, speed limit, 300,000 km per second. It's not just a good idea, it's the law. And yet, the universe itself seems filled with traffic blowing right past that sign. Galaxies 15 billion, 20 billion, 30 billion light-years away. Right now, they are all moving away from us faster than a beam of light could ever hope to catch them. This wasn't some minor disagreement. It was a full-blown paradox. The two great pillars of 20th-century cosmology, Einstein's relativity and Hubble's expanding universe, seemed to be telling us two completely different things. So what gives? Was Einstein wrong? Did he miss something? Or does Hubble's law just break down at extreme distances? For a while, this was one of the biggest puzzles in science. It was like the universe handed us two fundamental truths that couldn't both be true at the same time. Solving this would require a loophole in Einstein's law, a loophole the size of the entire universe. The great cosmic loophole: it's not what you think. The solution to this paradox is both incredibly elegant and totally counterintuitive. It turns out that Einstein was right, and Hubble was also right. The universe is expanding, galaxies are receding from us faster than light, and yet, the cosmic speed limit is not being broken. How? The secret is in what it means to move. Einstein's law is very specific. Nothing can move through space faster than light. But what if the object isn't moving through space at all? What if space itself is what's moving? That's the key. Those distant galaxies aren't firing up cosmic rockets and blasting through space. For the most part, they're just sitting pretty still in their own local neighborhood. The reason they're moving away from us is because the fabric of spacetime between us and them is expanding. This is called metric expansion, and it's a core prediction of Einstein's own theory of general relativity. His equations show that space isn't just an empty void, it's a real, dynamic thing that can stretch. The classic analogy is raisin bread. Imagine a lump of dough with raisins scattered throughout. You put it in the oven, and the whole loaf starts to expand. From the point of view of any single raisin, all the other raisins are moving away. A raisin an inch away might now be 2 inches away. A raisin 2 inches away might now be 4 inches away. The farther the raisin, the faster it seems to move. But here's the crucial part. Are the raisins actually moving? Not really. They aren't crawling through the dough. They're just being carried along as the dough itself expands. The raisins are galaxies, and the expanding dough is the fabric of spacetime. This is the cosmic loophole. Special relativity and its speed limit apply to motion through the dough. No raisin can race through the dough faster than light. But general relativity, which describes the dough itself, puts no speed limit on how fast the dough can expand. Space can stretch at any speed. So a distant galaxy isn't breaking the speed limit. The galaxy's own motion through its local patch of space, its peculiar velocity, is always far below the speed of light. But its recession velocity, the speed it moves away from us because of cosmic expansion, can be anything at all. This also neatly solves the cause and effect problem. If a galaxy is receding from us faster than light, then any light it emits today, aimed right at us, will never arrive. It's like trying to swim upstream against a current that's faster than you are. Even though the light is traveling at the speed of light relative to the space around it, that space is being carried away from us faster than the light can make progress. This creates a profound and slightly sad concept, the cosmic event horizon. It's a boundary out in space, currently about 16 billion light-years away. It's not a wall, but an information barrier. Any galaxy that drifts past that line is effectively gone from our future. We can still see the old light it sent out billions of years ago when it was closer, but anything happening in that galaxy right now is cut off from us forever. Its light will never reach us. We're watching the past of these galaxies play out, but their present and future are forever beyond our view. So the paradox is solved. Einstein's law is safe. Nothing moves through space faster than light. But the universe has a clever workaround. It just creates more space between things. Just when we thought we had our heads wrapped around that, however, astronomers found a shocking new twist. The expansion wasn't just happening, it was speeding up. The plot twist: the runaway universe. For decades after Hubble's discovery, the biggest question in cosmology was the universe's ultimate fate. We knew it was expanding, but gravity is a powerful brake. The pull of all the matter in the cosmos should be slowing the expansion down. Scientists saw two main possibilities. If there was enough matter and therefore enough gravity, the expansion would slow, stop, and then reverse, leading to a big crunch. If there wasn't enough matter, the expansion would slow down but never fully stop, leading to a cold, empty future called the Big Freeze. The whole debate was about which path we were on. To figure it out, astronomers needed to look deep into the past to see how fast the universe was expanding long ago. For this, they needed a special kind of stellar explosion, a type Ia supernova. These supernovae are even better, standard candles, than Cepheid stars. They happen when a white dwarf star in a pair sucks too much matter off its partner, goes over a critical weight limit, and erupts in a massive thermonuclear explosion. Crucially, they all explode with almost the exact same true brightness. This lets us measure their distance with incredible accuracy, even billions of light years away. In the late 1990s, two separate teams set out to do this. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were hunting for these distant explosions, trying to measure their brightness and redshift. They expected to find that the supernovae were a little brighter than they should be, which would prove that expansion was slowing down. What they found was the exact opposite. The distant supernovae were consistently dimmer than expected. They were farther away than they had any right to be. The only explanation was that the expansion of the universe hadn't been slowing down. For the last 5 or 6 billion years, it has been accelerating. The discovery was so stunning that the scientists spent months checking their work for errors. It seemed impossible. Something was pushing back against gravity and winning, forcing spacetime to fly apart faster and faster. In 2011, Perlmutter, Schmidt, and Rees won the Nobel Prize for discovering the accelerating expansion of the universe. Scientists gave a name to this mysterious, repulsive force: dark energy. What is dark energy? The simple and honest answer is, we have no idea. It's one of the biggest mysteries in science. It seems to be a property of space itself and energy of the vacuum. As the universe expands, matter and radiation get spread out and diluted. But dark energy's density seems to stay constant. This creates a runaway effect. More space creates more dark energy, which makes space expand even faster, which creates even more space, and on and on. This paints a wild picture of our cosmic future. The acceleration means that the cosmic event horizon, that boundary beyond which galaxies are lost to us, is getting closer. Galaxies we can see today will, one by one, cross that line and fade from our sky forever. In the far future, the universe will look like an increasingly dark and empty place, as all but our closest galactic neighbors are pushed away by this relentless expansion. The universe isn't just expanding, it's running away from us. The modern mystery, the Hubble tension. Just when it seemed things couldn't get any weirder, a new puzzle has popped up. A nagging problem known as the Hubble tension. The Hubble constant, h0, is the number that tells us how fast the universe is expanding today. Scientists have been working for decades to get its value just right. The problem is, depending on how you measure it, you get two different answers. There are two main approaches. The first is the late universe, or local, method. This involves looking at things relatively close to us, like the Cepheid stars and type Ia supernovae we've been talking about. Using amazing tools like the Hubble and James Webb Space Telescopes, astronomers have gotten a very precise number. About 73 kilometers per second per megaparsec. The second approach is the early universe method. This technique looks at the afterglow of the Big Bang, called the cosmic microwave background, CMB. Satellites like Planck have mapped this ancient light in stunning detail. By studying patterns in the CMB, cosmologists can use our best model of the universe to predict what the expansion rate should be today. This method consistently gives a lower value, around 67 or 68. That difference might not sound like much, but given how precise the measurements are, it's a really big deal. The error bars for the two results don't overlap. It's like measuring someone's height with a super accurate laser and a super accurate tape measure and getting two different answers. Something is off. This Hubble tension is now one of the hottest problems in cosmology. As of early 2026, data from the James Webb Space Telescope has strengthened the case for the local measurements, confirming the data is solid but not solving the tension itself. This makes the disagreement even harder to ignore. Are we missing something? Does dark energy change over time? Is there some new particle we don't know about? And there's a new player entering the game: gravitational waves from colliding black holes, used as standard sirens. While the results are still early, this new technique offers a completely independent way to measure the Hubble constant and might just be the tiebreaker. The universe, it seems, still has plenty of secrets. So, we come back to where we started. Einstein's one law. The speed of light is still the absolute speed limit for anything moving through space. It's a huge credit to his theories that, over a century later, this principle remains untouchable. But the universe plays a bigger game. The story of cosmic expansion is the story of a grand cosmic loophole. It shows us that space isn't a passive stage. It's an active player that can stretch and grow at unbelievable speeds. Because of this, distant galaxies are carried away from us faster than light, their present moments hidden forever behind a horizon we can never cross. And now, with the mystery of dark energy and the Hubble tension, we might be on the edge of another revolution in our understanding. The universe isn't just expanding. It's accelerating, driven by a force we can't explain, and maybe at a rate that our best theories can't predict. The law isn't broken, but the rules of the game are far more strange and wonderful than we ever imagined. The next time you look up at the night sky, remember what you're really seeing. You're looking across an ocean of expanding space, at ancient light from galaxies riding a current that's faster than light itself. You are a passenger on Spaceship Earth, on the fastest, most mysterious ride there is. The spacetime loophole that makes the impossible possible. In our universe, some laws feel absolute. One of them, a gift from Einstein, is beautifully simple. Nothing can travel through space faster than the speed of light. It's the ultimate cosmic speed limit. But what if I told you that, right now, huge chunks of our universe are absolutely demolishing that speed limit? That there are countless galaxies hurtling away from us at speeds that shouldn't be possible? This isn't a mistake. It isn't a miscalculation. And it isn't science fiction. This is a loophole. A secret written into the very fabric of space-time. A loophole that reveals the profound difference between moving through space and being carried along by the expansion of space itself. Because of this loophole, there are parts of our own universe that are, and will forever be, impossible for us to reach. They are lost to us, separated by an ever-expanding gulf of pure space-time. So today, let's dive into this paradox. We'll explore how the universe can break its most sacred law without actually breaking it at all. And by the end, you'll see the cosmos not as a static backdrop, but as a living, stretching, and ultimately unknowable place. The unbreakable law. To really feel the punch of this cosmic loophole, we first have to build up the wall it's about to break through. We need to understand why the speed of light isn't just a guideline, it's a fundamental pillar of reality. In the early 20th century, Einstein's theory of special relativity completely rewrote the rules. Before him, we thought space and time were separate things. A meter was always a meter, a second was always a second, for everyone. Einstein blew that idea apart. He showed that space and time are woven together into a single, four-dimensional fabric, space-time. And how you move through that fabric has some seriously weird consequences. One of the big ones is that as you accelerate something with mass, its effective mass actually increases. Think of it like the universe is pushing back. The faster you try to move something, the harder it gets to push. Its inertia grows. As you get closer and closer to the speed of light, that resistance becomes enormous. An object's mass would rocket towards infinity, and you'd need an infinite amount of energy to give it that final nudge. Good luck finding that. This means anything with mass can get incredibly close. 99. 999% of the way there, but it can never, ever cross that finish line. Only massless particles, like the photons that make up light itself, can travel at this ultimate speed. For them, it's the only speed they know. But there's an even deeper reason for this cosmic speed limit. It isn't just about speed, it's about cause and effect. It's the speed of information. If you could send a signal faster than light, you could shatter the logic of reality. You could get a reply to a message before you even sent it. You could know an event's outcome before it happened. This creates paradoxes that would unravel the universe. So, reality protects itself by enforcing that strict speed limit. So the law is set. Nothing with mass can reach light speed, and no information can travel faster than it. It's a clean, rigid, and seemingly unbreakable law that defines what's possible and what's impossible. For nearly a century, we thought that was the end of the story. But the universe is a far stranger place than we ever imagined. And when we pointed our telescopes to the sky, we found something that seemed to spit in the face of Einstein's perfect law. We found evidence of the impossible. The cracks in certainty. The first crack in that solid wall of certainty showed up back in the 1920s, thanks to an astronomer named Edwin Hubble. Hubble was spending his nights looking at these faint, fuzzy blobs in the sky that were then just called nebulae. No one knew for sure what they were. Were they just gas clouds inside our own Milky Way? Or were they entire, island universes? Galaxies just like ours, but incredibly far away. Using the world's most powerful telescope at the time, Hubble zoomed in on one of these smudges, the Andromeda Nebula. He was able to see individual stars, and by focusing on a special type called Cepheid variable stars that pulse at a rate tied to their true brightness, he could calculate how far away they were. The answer he got was staggering. Andromeda wasn't a local gas cloud, it was almost 1,000,000 light-years away, placing it far outside the Milky Way. In that moment, the known universe went from just one galaxy to countless galaxies. But that was just the start. As Hubble studied these new galaxies, he looked at their light. He used spectroscopy, a technique that splits light into a rainbow of colors. Inside that rainbow are dark lines, like a barcode, showing what chemical elements are in the galaxy. What Hubble saw was that for almost every galaxy, that barcode was shifted towards the red end of the spectrum. This is called redshift. We're all familiar with something similar in sound, the Doppler effect. An ambulance siren sounds high-pitched as it comes towards you because the sound waves are compressed, and low-pitched as it moves away because they're stretched. Hubble interpreted this galactic redshift the same way. A shift to red meant the light waves were being stretched, meaning the galaxies were moving away from us. He then found a clear pattern. The farther away a galaxy was, the bigger its redshift. And that meant the faster it was moving away from us. The conclusion was stunning. The universe was expanding. Hubble boiled this all down into one simple formula that would change cosmology forever. Hubble's law. It says a galaxy's speed is just its distance from us multiplied by a number called the Hubble constant. At first, this was just a neat discovery. But as our telescopes got better and we could see even deeper into space, a terrifying paradox started to crawl out of that simple equation. The Hubble constant measures how fast the universe is expanding. Right now, our best measurements put it around 70 kilometers per second per megaparsec. A megaparsec is just a big unit of distance, about 3.26 million light-years. So for every 3.26 million light-years you go out, a galaxy is moving away 70 kilometers per second faster. That doesn't sound very fast. But the universe is huge, and that's where the math gets wild. A galaxy 100 megaparsecs away is receding at 7,000 km per second. At 1,000 megaparsecs, that's 70,000 km per second, nearly a quarter of the speed of light. And if you just keep going, You eventually hit a distance where the math predicts the impossible. At about 14 billion light-years away, Hubble's law predicts a galaxy is moving away from us at the speed of light. And beyond that? Galaxies farther than 14 billion light-years away should be receding faster than the speed of light. Our observable universe stretches out to 46.5 billion light-years in every direction. That means the vast majority of the galaxies we can see are, right now, breaking the cosmic speed limit relative to us. So, here was the paradox. Einstein's special relativity says nothing can move through space faster than light. But Hubble's expanding universe shows us a cosmos full of galaxies that are doing just that. How can both be true? Is Einstein wrong? Or is something much, much weirder going on with space itself? The solution didn't come from tearing down the laws of physics, but from finding the secret loophole. The ultimate analogy: solving the paradox. The solution to this giant contradiction is one of the most beautiful, mind-bending ideas in all of science. It all comes down to a crucial difference: the difference between moving through space and the expansion of space itself. To get your head around this, let's use the classic cosmology analogy. A loaf of raisin bread dough rising in an oven. Picture that dough as the fabric of spacetime. The raisins scattered inside it are the galaxies. Now, as the loaf bakes, the whole thing expands. If you're sitting on one raisin, what do you see? You see all the other raisins moving away from you. A raisin that was an inch away is now 2 inches away. A raisin that was 2 inches away is now 4 inches away. The farther away a raisin is, the faster it seems to recede. Why? Because there's more dough, more space-time between you and it to expand. And here's the light bulb moment. The raisins aren't actually moving through the dough. They aren't firing up tiny engines and plowing through the bread. They're sitting still inside the dough. They're being carried apart because the dough itself, their reality, is stretching. This is exactly what's happening in our universe. That distant galaxy isn't rocketing through space at impossible speeds. Locally, it's probably just drifting along. The incredible speed we measure is the combined effect of all the tiny stretches of space between that galaxy and us. Each little bit of space expands by a tiny amount, but over billions of light-years, it all adds up to a faster-than-light recession. And that's the loophole. That's how the universe cheats. Einstein's speed limit from special relativity applies to objects moving within spacetime, the raisins traveling through the dough. But his bigger theory, general relativity, says spacetime itself is a dynamic thing. It can stretch, bend, and warp. And there is no known speed limit on how fast spacetime itself can expand. The speed of light is a * local speed limit. It's like the rule for a head-to-head race. Nothing can outrun a beam of light passing right by it. But the expansion of the universe is a * global phenomenon. It's not about the speed of the runners, it's about the racetrack itself stretching out underneath them. Think of it this way. An ant is on a very long, stretchy rope. The ant has a top speed it can crawl. That's its local speed of light. Now, two people start stretching that rope from both ends. If they stretch it fast enough, the ant's destination will move away from it faster than the ant can crawl. The ant isn't breaking its own speed limit. The space it's walking on is just expanding so fast that its journey becomes impossible. This is exactly what happens to light from a galaxy receding faster than light. A photon leaves that galaxy, heading towards us at the speed of light. But the space it's traveling on is like a treadmill moving in the opposite direction. And for the most distant galaxies, that treadmill of space is pulling away faster than the photon can run towards us. It's fighting a losing battle. So, the paradox is solved. Galaxies aren't breaking any laws. Einstein was right. Nothing is moving through space faster than light. But space itself is expanding, carrying everything with it, and that changes our entire map of the cosmos. The new cosmic map. Getting this loophole means we have to completely redraw our map of the universe. It's a place with different zones and boundaries, defined not by walls, but by the limits of light and time. These are the cosmic horizons. First up is the one we know best, the observable universe. This is everything we can possibly see. The universe is about 13.8 billion years old, so you might think this is a sphere 13.8 billion light years across. But that doesn't account for expansion. When you factor in all the stretching that space has done over that time, the true edge of the observable universe is about 46.5 billion light years away. Everything inside this 93 billion light-year wide bubble is theoretically visible, because its light has had enough time to reach us. Now for a new boundary. The Hubble sphere. This is where the expansion of space itself hits the speed of light. Right now, that boundary is about 14 billion light-years away. Everything inside this sphere is receding from us slower than light. Everything outside it is receding faster than light. And here's where it gets really weird. You'd think we can't see anything outside the Hubble sphere, right? Because it's moving away faster than light. But you can, and we do. How is that possible? Remember, we see distant galaxies as they were in the past. If we see a galaxy that's now 30 billion light years away, and way outside our Hubble sphere, the light we're seeing today left that galaxy billions of years ago. Back then, the galaxy was much closer to us and was inside the Hubble sphere. Imagine a boat trying to get to a waterfall. The boat is a photon, and we're at the waterfall. A galaxy way upriver, and receding faster than the boat's top speed, drops the boat in the water. At first, the current is so strong it carries the boat backwards, away from us. But the river current is slower closer to the waterfall. As the boat is carried along, it eventually drifts into a region where its own speed is finally faster than the current. From there, it can make progress and eventually reach us. In the same way, light from a superluminal galaxy started its journey when it was inside the Hubble sphere. It fought against the current of expanding space until it crossed into our local region, where expansion is slower, allowing it to finally reach our telescopes. This brings us to the final, most absolute boundary, the cosmic event horizon. This is the true point of no return. The expansion of the universe is accelerating, thanks to a mysterious thing we call dark energy. The cosmic event horizon is the line in the sand. Any event that happens beyond this line right now will produce light that can never, ever reach us. It's like the river current is now speeding up everywhere, and boats launched too far away will be swept away forever, no matter how hard they paddle. That horizon is currently about 16 billion light years away. To be clear, we can see galaxies that are now located far beyond that, but we're only seeing their ancient light. Any new light they emit, any star that explodes there today, is information we will never get. In their present moment, they are completely cut off from us. They have crossed a boundary into a part of reality that is forever locked out of our future. A universe of ghosts and memories. This new cosmic map forces us to face a deep, and kind of lonely, reality. When we look deep into the sky, we're not just looking across space, we're looking back in time. But more than that, we're looking at a universe of ghosts. Think about a galaxy at the very edge of our observable universe. The light we see from it has traveled for over 13 billion years. It shows us a baby galaxy, one of the first to ever exist. But where is that galaxy now? After 13 billion years of cosmic expansion, it's now about 46 billion light years away, receding at a speed far faster than light. The galaxy we see is just a memory. Its present self is living in a patch of spacetime that is totally inaccessible to us. We're looking at a photograph of a place we can never go. So, looking at these distant objects is kind of bittersweet, isn't it? The very light that lets us discover them is also their final goodbye. As cosmic expansion accelerates, more and more galaxies are crossing that cosmic event horizon. One by one, galaxies that we can see today will appear to freeze in time from our point of view, their light stretching out until they just fade to black. Imagine the night sky in the far, far future. It's going to be a very different, and very lonely, place. Over trillions of years, every galaxy that isn't gravitationally bound to us will recede beyond the event horizon and disappear. The rich tapestry of galactic islands will vanish. Future astronomers in our own merged supergalaxy will look out and see nothing. Just an endless, empty darkness between their own stars. They would have no evidence of other galaxies. No hint of a Big Bang. No sign of cosmic expansion. The most basic truths of our cosmology will have been wiped from the sky. They would think they live in a single, static island universe, completely unaware of the grand, dynamic cosmos we are so lucky to see. It means that right now, we're living in a golden age of cosmology, a brief window in cosmic history where the evidence for our universe's origin is still written in the sky. The lingering mystery. Just when we think we have a handle on this cosmic picture, the universe throws us another curveball. Our whole understanding of this expansion is facing a crisis. It's a puzzle known as the Hubble tension. The rate of cosmic expansion is described by the Hubble constant. For decades, scientists have tried to nail down its exact value using two main methods. One team looks at the past. By studying the cosmic microwave background, the afterglow of the Big Bang, they can use our best model of the universe to predict what the expansion rate should be today. When they do this, they get a value of about 67 kilometers per second per megaparsec. Another team looks at the present. They use tools like the Hubble and James Webb Space Telescopes to directly measure the distances to nearby galaxies. It's a direct measurement of how fast things are moving away from us right now. But this method gives a different answer. About 73 kilometers per second per megaparsec. But 67 and 73 are not the same number. And their margins of error don't overlap anymore. That gap, that disagreement, is what scientists call the Hubble tension. Our two best ways of measuring the universe are giving us two different answers. It looks like the universe today is expanding 5 to 9% faster than our models predict. What could be causing this? The possibilities are thrilling. It might mean our understanding of dark energy is too simple. Maybe there's a new, undiscovered particle from the early universe that gave expansion a temporary boost. Some even wonder if it's the first clue that Einstein's theory of gravity isn't the final word on cosmic scales. We don't have the answer. But the Hubble tension tells us that not only is the cosmos stretching and creating these unreachable places, but it's doing it in a way we still don't fully understand. The loophole is real, but the engine driving it might be even stranger than we thought. So, let's bring it all back. Einstein's law holds true. Nothing can move through space faster than light. But the universe revealed a loophole. Space itself isn't bound by that law. The fabric of reality expands, and over huge distances, it carries galaxies away from us at impossible-seeming speeds. This isn't a flaw in our physics, it's a core feature of our reality. It carves the cosmos into regions we can see, regions we can only remember as ghosts, and vast, unknowable territories forever beyond our horizon. We live on a cosmic island, watching the light from other islands fade as the very ground of existence stretches out from under us. It's a humbling thought. We are lucky to live in a time when the universe's story is still visible in the sky. But we also have to accept that we will never, ever see the whole picture. Most of reality is simply impossible to reach. What does it feel like to know that most of the universe is forever beyond our grasp, not because of technology, but because of the nature of spacetime itself? Let me know your thoughts in the comments. If you found this journey as fascinating as I do, consider subscribing. There are endless mysteries out there, and we're going to keep exploring them. New evidence shows the universe is actually slowing down. For nearly 30 years, we've held on to one of the biggest discoveries in the history of science. The universe isn't just expanding, it's doing it faster and faster every second. We named the mysterious force behind it dark energy, a discovery so huge it won a Nobel Prize back in 2011. It painted a pretty bleak picture of our cosmic fate, a big freeze, or a big rip, where everything ends up torn apart in cold, empty darkness. But what if that whole story, the one we've been telling for a generation, was based on a cosmic illusion? What if the evidence was flawed? Because new, and very controversial, research that came out in 2025 suggests we may have gotten it all wrong. The latest data is hinting that the most powerful force in the universe is getting weaker, and the cosmos is actually hitting the brakes. The age of acceleration, a Nobel-winning discovery. To really get why this is such a huge deal, we need to jump back to the 1990s. For most of the 20th century, cosmology was all about a cosmic tug-of-war. In one corner, you had the Big Bang, the explosive push that sent everything flying apart. And in the other, you had gravity, the combined pull of everything in the universe, trying to reel it all back in. The biggest question was simple. Who wins? Would the universe expand forever, or would gravity eventually win out and pull everything back into a fiery, big crunch? For decades, astronomers were pretty sure they knew the answer. The universe, like a ball thrown in the air, should be slowing down. The only real question was whether it had enough oomph to escape its own gravity. To figure this out, scientists needed to measure the universe's expansion rate at different times in its history. If the universe was slowing down, it should have been expanding faster in the past than it is today. The key was finding standard candles, objects with a known, reliable brightness that could act as cosmic mile markers. If you know how bright something really is, you can tell how far away it is by how dim it looks. And the perfect tool for the job seemed to be a special kind of exploding star, a type Ia supernova. These explosions happen when a white dwarf star in a two-star system steals too much material from its partner. Once it hits a critical weight about 1.4 times the mass of our Sun, it triggers a massive thermonuclear explosion. And because they all supposedly blow up at the same mass, the theory was they all hit the same peak brightness. They were the uniform, cosmic lighthouses astronomers had been dreaming of. In the late 90s, two separate teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how much the universe was slowing down. They used powerful telescopes to hunt for these distant explosions, collecting data on dozens of them. But when they crunched the numbers, they found something that absolutely nobody expected. The distant supernovae were dimmer than they should have been. A lot dimmer. There was really only one way to explain it. They were farther away than all the models predicted. And for them to be farther away, the expansion of the universe couldn't be slowing down. It had to be speeding up. The announcement, back in 1998, was a complete shock. It was like throwing a ball in the air and watching it suddenly accelerate into space instead of falling back down. It went against everything we thought we knew about gravity. The implications were mind-boggling. If the expansion was accelerating, some invisible, repulsive force had to be pushing everything apart, a force strong enough to overpower the gravity of the entire cosmos. They didn't know what it was, so they gave it a name that fit: dark energy. This wasn't just a minor tweak. It was a revolution. Our picture of the universe's ingredients was flipped upside down. The normal stuff, stars, planets, you and me, made up less than 5% of everything. Around 25% was dark matter, another mystery substance that has gravity but doesn't interact with light. But the champion, the vast majority at nearly 70% of the cosmos, was this new, strange dark energy. The standard model of cosmology was rewritten. It became the lambda CDM model, where the Greek letter lambda, stood for this constant, unrelenting dark energy. The model was a huge success. It perfectly explained the supernova data and fit with other major observations, like the faint afterglow of the Big Bang. For their paradigm-shifting work, the leaders of the two teams were awarded the Nobel Prize in Physics in 2011. The accelerating universe wasn't just a theory, it felt like a fact. For the next 25 years, this was the story. A cosmos born in fire, slowed by gravity for a while, but now in the grip of a runaway expansion. Our ultimate fate seemed set. A big freeze, where the universe grows into a cold, desolate void, or maybe a big rip, where the expansion becomes so violent it tears apart atoms themselves. A dark, lonely conclusion. But science is never really settled. It's a process of constant questioning. And hiding in plain sight was a potential flaw in the very foundation of this entire story, a problem with the lighthouses. The anomaly, the faint and faltering clues. The entire argument for an accelerating universe hinged on that one critical assumption. That Type Ia supernovae are perfect, standard candles. That they all have the same intrinsic brightness, no matter when or where they exploded in the universe's 13.8 billion year history. Astronomers worked hard to correct for things like dust that might get in the way, but what if the assumption itself was flawed? What if the lighthouses weren't all the same? This is where our story takes its dramatic turn, in the year 2025. A team of astronomers led by Professor Young-Wook Lee of Yonsei University in South Korea published a study looking not just at the supernovae, but at the galaxies they exploded in. And they asked a simple, yet game-changing question. Does the age of the stars in the host galaxy affect the brightness of the supernova? Think about it. A supernova is a star's grand finale. The stars blowing up in the distant universe are from an earlier, younger era. They have a different chemical makeup than stars exploding closer to us, in older galaxies. The early universe hadn't been seeded with as many heavy elements that are forged inside stars and spread by, you guessed it, supernovae. So, could this difference in what the stars are made of affect the explosion itself? The Yonsei University team analyzed hundreds of supernovae and their host galaxies. And what they found sent shockwaves through the world of cosmology. They discovered a clear correlation. Even after all the usual corrections, supernovae that blew up in younger galaxies, the kind found in the early universe, were naturally fainter than those that exploded in the older galaxies nearby. The importance of this can't be overstated. The team reported their finding with an extremely high level of statistical confidence, what's known as a 5 sigma result, the gold standard for a major discovery. It meant that a huge part of the dimming that the Nobel-winning teams saw wasn't from cosmic acceleration at all. It was just a feature of the supernovae themselves. The lighthouses weren't standard, their brightness changed with age. One of the researchers said the original discovery was like doing up a shirt with the first button fastened incorrectly. No matter how carefully you do the rest, the whole shirt is crooked. Here, the first button was assuming all supernovae were identical. By missing this age-related bias, we may have been misreading the signs for decades. This new idea was strengthened by a flood of data from next-generation surveys, especially the Dark Energy Spectroscopic Instrument, or DESI. DESI is creating the largest 3D map of the universe ever made, and it measures cosmic expansion using a totally different method called baryon acoustic oscillations, BAO. BAOs are basically giant ripples, sound waves that were frozen into the fabric of space shortly after the Big Bang. They give us a standard ruler of a known size. By measuring how big this ruler appears at different distances, astronomers can independently map the history of cosmic expansion. And here's the kicker. When the Yonsei team's corrected supernova data was analyzed, it suddenly agreed much better with the expansion history measured by BAO and other early universe methods. For years, there has been a nagging problem called the Hubble tension, where measurements of the expansion rate today give a higher number than measurements from the early universe. This new, corrected data seemed to shrink that gap. By fixing what might have been an unreliable witness, the supernovae, the story they told started to line up with the other evidence. The foundation of the accelerating universe was cracked. The new reality, the great slowdown. So, if the supernovae in the early universe were just naturally fainter, the whole story of acceleration starts to unravel. The original evidence was that these distant explosions were about 25% dimmer than expected. The Yonsei team's analysis suggests that a big chunk of that dimming, maybe even most of it, wasn't from the universe speeding up, but was just an artifact of how stars evolve. Once you correct for that bias, the evidence for acceleration doesn't just get weaker. According to this study, it disappears. In fact, the data starts to point in the opposite direction. According to this new analysis, when you combine the corrected supernova data with the more robust measurements from BAO, the standard model of a constantly accelerating universe is seriously challenged. The combined data instead points to a universe that isn't accelerating today. It may have already transitioned back into a state of decelerated expansion. That cosmic tug of war isn't over. It looks like gravity might be starting to win again. This is a conclusion so profound it's hard to wrap your head around. It suggests dark energy isn't a cosmological constant, an unchanging property of space, as Einstein once imagined. Instead, it would have to be something dynamic, something that evolves. This idea, called quintessence, pictures dark energy as a field that can change over time. The new data implies this field is getting weaker. The mysterious anti-gravity that has been running the show for billions of years is losing its punch. This changes everything, especially our cosmic fate. The Big Freeze, or Big Rip, is suddenly no longer a sure thing. If dark energy is weakening and the universe is slowing down, a whole new set of endings are possible. One idea is that the universe will just coast forever, slowly fading out. But another, far more dramatic possibility is now back on the table: the Big Crunch. If dark energy keeps getting weaker, its repulsive force could eventually lose the fight against gravity. At that point, the expansion would stop. And then, it would reverse. Galaxies would stop flying apart and start falling back together. Over billions of years, the cosmos would contract faster and faster, pulling everything back into a single, infinitely hot and dense point, a mirror image of the Big Bang. The idea of a cyclical universe, one that goes through endless cycles of big bangs and big crunches, is ancient, but it was mostly abandoned when acceleration was discovered. This new evidence breathes fresh life into it. It suggests our universe might not have a one-way ticket to oblivion, but could be part of a cosmic cycle of death and rebirth. We can't be sure this will happen, but the fact that it's once again a real possibility is a monumental shift. This new model also offers a path to solving the Hubble tension. By correcting the supernova data, the late universe measurement of the expansion rate moves closer to the early universe value. The conflict doesn't completely go away, but it's significantly reduced. It suggests the tension wasn't a flaw in our physics, but a flaw in our tools. We were trying to measure the cosmos with a bent ruler. The resolution. The unwritten future. So, is the accelerating universe officially dead? Are we headed for a big crunch? The answer, for now, is an exciting maybe. This is science working as it should. The 2025 papers don't represent the final word, but the opening shot in a new and incredibly important debate. Claiming a Nobel Prize-winning discovery was based on a fundamental error is a huge deal, and it requires an incredible amount of evidence. As you'd expect, the findings have been met with a lot of healthy skepticism. Cosmologists everywhere are now digging into the analysis, rechecking the data, and designing new ways to test these results. The original teams that discovered dark energy are almost certainly reanalyzing their own data. Other independent groups will try to replicate the findings. The beauty of science is that it doesn't rely on just one study. It's a global effort to get closer to the truth. What is certain is that our understanding of dark energy has been shaken. For years, the lambda CDM model has been our comfortable standard. But even before this, cracks were showing. The Hubble tension was a big one. And data from Daisy was already dropping hints that dark energy might not be constant. The Yonsei University study didn't appear out of thin air. It provided a key that might just unlock these other mysteries. The next few years are going to be pivotal. The future of this debate hangs on more data. Daisy is only partway through its mission and will eventually map over 40 million galaxies, giving us an even more precise history of expansion, completely independent of supernovae. Even more exciting is the flood of data we expect from the Vera C. Rubin Observatory. This new telescope will survey the sky for a decade, discovering tens of thousands of new supernovae. With that massive dataset, scientists can test this age-brightness connection with unbelievable precision. It will be the ultimate fact check. We are living in the middle of a potential scientific revolution. For over 2 decades, we were confident in the story of a universe running away from us. Now, that story is up for grabs. The universe might not be accelerating into a cold, dark future. It might be slowing down, maybe even heading for a fiery rebirth. This uncertainty isn't a failure. It's the thrill of the chase. It's the reminder that the universe doesn't owe us a simple story. For the first time in a generation, we have to admit, we have no idea how the story is going to end. What do you think this means for the future of our universe? A slow fade into darkness, or a fiery big crunch? Let us know your thoughts in the comments below. And if you enjoy unraveling the biggest mysteries of the cosmos, make sure to subscribe and hit the notification bell so you don't miss our next deep dive. The journey to understand our universe is a long and winding one. For a while, it seemed like we were on a straight road to a clear destination. But this new evidence has shown us there are unexpected twists and turns. The idea that the universe is slowing down challenges one of the biggest discoveries of the last century. It forces us to rethink everything. The debate is far from over, but one thing is certain. The universe just got a whole lot more interesting. The terrifying truth about reaching the edge of space. What do you picture when you think about the edge of the universe? A solid wall? An endless, silent void? Maybe a shimmering curtain separating our reality from something else? For as long as we've looked up, we've wondered where it all ends. We're explorers. It's in our DNA. We have an insatiable need to know what's over the next hill, across the next ocean, and beyond the next star. The edge of the universe is the ultimate destination. But what if the truth of that final frontier is far stranger, more profound, and honestly, more terrifying than anything you could imagine? What if you spent billions of years crossing the darkness, only to discover the edge you were looking for doesn't exist? Not in any way you think. What if, instead of a boundary, you found a truth so mind-bending it shatters the very idea of location, distance, and even outside? This isn't just a thought experiment. This is the staggering reality our best science points to. And our journey to understand it starts not billions of light years away, but right here, just above our heads. Because before we can talk about the edge of the asterisk universe, we have to talk about the edge of space. The title of astronaut and the laws of the sky all depend on a line you can't even see. Most agree it's the Kármán line about 100 kilometers or 62 miles up. This is the point where the atmosphere becomes so thin that airplane wings no longer work. To go higher, you can't fly, you have to orbit. But even this first, most basic edge is up for debate. NASA and the US military say it's lower, around 80 kilometers, or 50 miles. The truth is, there's no hard border. The sky just fades to black. This first edge isn't a wall, it's a fuzzy, human-defined transition zone. And that's the first and most important clue on our journey today. The cosmos doesn't do neat and tidy borders. Prepare yourself, because we're about to find out what it means to live in a universe without a real edge. The journey begins, leaving home. Once we cross that disputed line and the familiar blue sky gives way to the black of space, we look back. Earth shrinks behind us, becoming that famous, pale blue dot, a fragile speck of light hanging in a vast, silent arena. That view is lesson 1. A humbling gut punch about our own scale. Our entire world, all of our history, is just a single pixel in the cosmic photograph. Our journey takes us through our solar system, past the cratered face of the Moon and the rusty plains of Mars. We pass the gas giants. Jupiter, a swirling behemoth with a storm bigger than our planet, and Saturn, with its impossibly elegant rings, a breathtaking testament to gravity and motion. Each planet feels like a milestone, but the overwhelming reality of this trip is the emptiness. The distances are brain-breaking. It took the Voyager probes, some of the fastest things we've ever built, over 30 years just to get to the edge of this system. For years on end, the view from our ship would be an unchanging black canvas, punctuated only by the rare flyby of a distant world. Beyond Neptune, we reach what you might call the first edge of our solar system, the Kuiper Belt. It's not a wall, but a vast, donut-shaped ring of icy bodies, Pluto being the most famous resident. Crossing it is just a slow, gradual process where the space junk thins out. But we push further, into the truly remote Oort cloud. First theorized by Jan Oort in 1950, this is the Sun's real gravitational boundary. It's a gigantic, spherical shell of trillions of icy objects, like a thick bubble surrounding our solar system, possibly stretching out over a light year or more. The Sun's grip is so weak out here that a nudge from a passing star can send one of these ice balls on a million-year journey toward us, which we then see as a comet. This is our first real encounter with a cosmic edge, and it teaches us a critical lesson. The edge of the solar system isn't a line. It's not a fence. It's a vast, spherical zone defined only by the fading whisper of our star's gravity. You could fly right through it and not even notice. The blackness would look the same. You'd only know you'd crossed the border by checking your instruments. This is our first big clue that our earthly ideas about boundaries are useless out here. We've left our solar system, only to find ourselves in an even bigger emptiness. The void between the stars. The galactic sea, crossing the Milky Way. With the Sun now just another bright star behind us, we are truly adrift in the galactic sea. And here, the scale of things just explodes. We no longer measure distance in miles or even in how long it takes to fly to Jupiter. The only unit that makes sense is the light year, the nearly 6 trillion miles light travels in 1 year. The nearest star, Proxima Centauri, is over 4 light years away. Our ship, even at impossible speeds, would spend millennia just crossing the gaps between stars. This interstellar space isn't a perfect vacuum. It's a thin soup of gas, dust, and cosmic rays, but it's emptier than anything we can create on Earth. As we journey on, we start to see the grand structure of our home galaxy, the Milky Way. From the outside, it's a spectacular pinwheel of light and dust, 100,000 light years across and home to somewhere between 100 and 400 billion stars. We head inward first, toward the galactic core. The sky, once mostly black, begins to glow with the light of countless suns. At the very center is a monster. Sagittarius A*, a supermassive black hole with the mass of 4 million suns, the gravitational anchor for our entire galaxy. We steer clear of that point of no return and turn our ship around, heading for the galactic rim. We cross vast clouds of gas and dust where new stars are being born, magnificent nebulae lit up by hot, young stars. We pass ancient star clusters, dense balls of millions of stars orbiting together for eons. As we near the outer edge of the galactic disk, the stars begin to thin out again. The brilliant spiral arms fade behind us as we enter the galactic halo, a vast, spherical region of scattered, ancient stars and mysterious dark matter. Finally, we reach the edge of the Milky Way. And just like the solar system, there's no signpost. The number of stars simply dwindles, becoming more and more sparse until we are looking back at a colossal, swirling island of light in an infinite ocean. We've crossed a second, much bigger, edge, and the lesson is hammered home. Cosmic edges aren't walls, they're just places where stuff fades away. We've traveled hundreds of thousands of light years. We've left our star and our galaxy behind. And what do we find? More space. An emptiness even more profound. We are now in the great cosmic web, the largest structure known, and we're about to run into an edge of a completely different kind. The great cosmic web, the observable universe. Out here, in the void between galaxies, the word distance almost loses its meaning. The Milky Way shrinks to a single point of light, joining countless others that aren't stars, but entire galaxies. Our nearest major neighbor, Andromeda, is over 2.5 million light-years away. From this vantage point, we can finally see the universe on its largest scale. It isn't just a random scattering of galaxies. They're arranged in a magnificent, intricate structure known as the cosmic web. Galaxies clump into groups and superclusters, which form long, massive filaments stretching for hundreds of millions of light-years, surrounding vast, dark, empty regions called voids. It looks like a sponge, or a network of neurons, a glowing web of matter against an almost absolute blackness. And it's here that we find our first real candidate for an ultimate edge, the boundary of the observable universe. This is a totally different concept. It's not an edge made of matter, but an edge made of information. The universe began about 13.8 billion years ago in the Big Bang. Because light travels at a finite speed, there's a maximum distance from which light has had time to reach us. This creates a spherical bubble around us, with us at the center, with a radius of about 46.5 billion light-years. It's bigger than 13.8 billion light-years because space itself has been expanding the whole time. Anything beyond this cosmic horizon is invisible to us, simply because its light hasn't had enough time to get here yet. This sounds like a final edge. But here's the twist. This edge is centered on us. An alien in a galaxy a billion light-years away would have their own observable universe, their own bubble, centered on them. They'd see parts of the cosmos we can't, and we see parts they can't. The edge of the observable universe isn't a fixed wall in space. It's a personal horizon that depends entirely on where you are. This bizarre, moving edge is a direct result of the expansion of the universe. Back in the 1920s, Edwin Hubble discovered that nearly all galaxies are moving away from us, and the farther away they are, the faster they're moving. A common mistake is to picture this like an explosion, with everything flying out from a center point. That's wrong. The galaxies aren't flying through space. Space itself is stretching, carrying the galaxies along for the ride. Imagine dots on the surface of a balloon. As you inflate it, all the dots move away from each other. From any one dot's perspective, all the other dots are receding. The weird part is, there's no center to this expansion. Every point is the center. Every observer in every galaxy sees the exact same thing. This stretching of space also stretches the light traveling through it, shifting it toward the red end of the spectrum. This is called cosmological redshift. Our journey toward the edge of the observable universe is a journey into an increasingly redshifted reality. We're chasing a horizon that's defined by the very fabric of reality expanding everywhere. And that leads to the most unsettling part of all. The speed of nothing, faster than light expansion. Our journey now gets truly weird. We know that the farther away a galaxy is, the faster it recedes. Double the distance, double the speed. This leads to a staggering conclusion. There must be a distance where galaxies are receding from us at the speed of light. This is called the Hubble sphere, about 14.4 billion light-years away. Anything beyond that is carried away from us by the expansion of space faster than the speed of light. Wait, hold on. Didn't Einstein say nothing can travel faster than light? Yes and no. His theory of relativity says nothing can move through space faster than light, and that rule holds. These galaxies aren't firing their rockets. The faster than light speed is caused by the expansion of space itself. Imagine two raisins in a loaf of rising bread. If they're far enough apart, the dough between them can expand fast enough that their separation speed is greater than the speed a single raisin could ever move through the dough. There is no speed limit on the expansion of space. This has a terrifying consequence. Take a galaxy just beyond our Hubble sphere. It emits a photon of light aimed right at us. That photon travels through space at the speed of light, but the space it's traveling through is being stretched away from us even faster. It's like trying to run up a down escalator that's moving faster than you can run. You will never reach the top. This means that the light from galaxies beyond a certain point, the cosmic event horizon, about 16 billion light-years away, will never reach us. Ever. Those galaxies are causally disconnected from us. We are seeing them now with light they emitted billions of years ago, but the light they are emitting today is being swept away by the cosmic tide, lost to us forever. There are entire realms of the universe, possibly with countless civilizations, that we can never visit, never talk to, and never even know are there. The universe isn't just expanding, it's tearing itself into isolated islands of spacetime. And it gets worse. Recent measurements from telescopes like Hubble and JWST show the universe is expanding faster today than our models based on the early universe predict. This Hubble tension suggests some mysterious force, which we call dark energy, is accelerating the expansion. This means galaxies are slipping beyond our reach even faster than we thought. In a very real sense, the part of the universe we can ever hope to see is shrinking. The wall of fire, reaching the edge of time. As we keep pushing outward, something strange happens. We're not just traveling through space anymore, we're traveling through time. The light from a galaxy 10 billion light-years away has been traveling for 10 billion years. We are seeing it as it was 10 billion years ago. Our journey to the edge of space has become a journey to the beginning of time. The galaxies we see now look different. They're not the tidy spirals of our local universe. They're smaller, chaotic, and bright blue, blazing with furious star formation. We are witnessing the universe in its violent youth. Pushing further, we fly past the most distant galaxies ever seen by JWST, back to when the universe was just a few 100 million years old. Eventually, we reach a point where there are no more galaxies. No stars. We've gone so far back in time that we've arrived before the first stars ever ignited. This is the cosmic dark ages. For hundreds of millions of years, the universe was just a dark, churning expanse of hydrogen and helium gas. But this still isn't the end. If we keep going, we finally hit a wall. Not a wall of matter, but a wall of light. An opaque, glowing fog that fills all of space. This is the cosmic microwave background, CMB*. For the first 380,000 years after the Big Bang, the universe was an incredibly hot, dense soup of particles and light. Photons couldn't travel freely. They were constantly scattering off free electrons. The whole universe was an impenetrable, glowing fog. Then, at the 380,000 year mark, the universe cooled enough for electrons to combine with nuclei to form the first atoms. Suddenly, the photons were free. The universe became transparent. The CMB is the first light from that moment. It's a photograph of the infant universe, a glowing wall of light that surrounds us in every direction. Over 13.8 billion years of cosmic expansion, that light has stretched and cooled from a blazing 3,000 Kelvin to a mere 2.7 Kelvin above absolute zero, a faint microwave hum. This is the ultimate edge of what we can see. We can never build a telescope that sees past the CMB, because the universe itself was opaque before then. It is a boundary in time. Our journey outward in space has led us to a glowing wall that marks the afterglow of creation itself. The terrifying truth. Beyond the horizon. So we're here. At the final barrier. A wall of light from the dawn of time. This is the edge of everything we can see. What happens if our ship tries to cross it? The answer is the most profound and unsettling revelation of all. Nothing. Absolutely nothing happens. As we continue to travel, the cosmic microwave background, that wall of ancient light, would simply stay ahead of us, always at the same distance. The edge of the observable universe is a bubble of information centered on us. As we move, the bubble moves with us. Think of it like this. You're on a ship in the middle of the ocean. The horizon is a perfect circle around you, the edge of your world. If you sail toward it, you don't crash into a wall. The horizon just moves with you. You are now at the center of a new circle, seeing parts of the ocean you couldn't see before, while the part you left has slipped over the horizon behind you. That's exactly what happens on a cosmic scale. As we travel, new regions of the universe would come into view ahead of us, while the places we left behind would eventually recede over our cosmic horizon, their light lost to us forever. The edge of the universe is not a place. It's a perspective. An illusion created by the finite speed of light and the finite age of the cosmos. That is the terrifying truth. We went searching for a boundary, and we found that the very concept is meaningless. There is no center to the universe, and there is no edge. So what's beyond the part we can see? The simplest answer is just more of the same. More galaxies, more clusters, more voids, stretching on and on. But how far? Is it finite or infinite? Our best measurements suggest the universe is flat, meaning it follows the rules of geometry we learned in school. A flat universe could be infinite, stretching on forever. If that's true, the Big Bang didn't happen at a point. It happened everywhere at once in an already infinite space. Or, a flat universe could be finite but unbounded. Think of the surface of a donut. It's finite, but it has no edge. If you walk in a straight line, you'll eventually loop back to where you started. Our three-dimensional universe could be a more complex version of that. Travel far enough in one direction, and you might just end up right back where you started. We don't know which is true. The universe is at least hundreds of times bigger than the part we can see, but whether it's truly infinite is beyond our ability to measure. If this journey to the edge of reality bent your mind a little, hit that subscribe button. We tackle the biggest questions in science every week. And let us know in the comments. What cosmic mystery keeps you up at night? We started this journey looking for an end, a final shore to the cosmic ocean. We traveled past stars, across galaxies, and back to the dawn of time itself. But we found no such thing. Instead, we found a reality where space can stretch faster than light, creating cosmic islands forever cut off from each other. We found a horizon that isn't a wall, but a trick of perception that moves with us wherever we go. The terrifying truth about reaching the edge of space is that there is no edge to reach. The terrifying truth is that our most basic ideas of location, of boundaries, of an outside or local illusions, born on a tiny rock in a quiet corner of a cosmos that is incomprehensibly vast. The universe isn't a container, it is the container. It's either infinite or it loops back on itself, but either way, it's boundless. The ultimate revelation isn't that we are small. It's that the universe operates on a logic that transcends our intuition. We are products of the cosmos, trying to understand a reality that is under no obligation to make sense to us at all. And in that humbling, awe-inspiring, and slightly terrifying realization lies the true wonder of our place in it. The cosmic race light can never win. Imagine the greatest race ever. The track isn't asphalt, it's the fabric of reality itself. The starting gun fired 13.8 billion years ago. And the runner is the fastest thing there is. A photon of light, moving at the absolute, unbreakable speed limit of the cosmos. But this is a strange race. Because in this race, the finish line is running away from the runner, faster than the runner can possibly move. This isn't a riddle. It's the staggering, counterintuitive reality of our universe. We look up at the night sky and see the ghosts of distant galaxies. Their light has traveled for billions of years to reach our telescopes, like postcards from a long-lost era. We see them. We can measure them. And yet, at the very moment we're observing them, many of these same galaxies are running away from us at speeds that defy comprehension, speeds greater than the speed of light. How is that possible? How can we see something that's currently moving away from us faster than its own light can travel toward us? This paradox gets to the very heart of our understanding of reality. It challenges the one rule we thought we knew. Nothing is faster than light. But it turns out, the universe has a loophole. A big one. The truth isn't that light is losing a simple foot race. It's far more profound. The racetrack itself, the very space between us and everything else, is expanding. It's stretching, carrying galaxies along for the ride, and creating more distance with every passing moment. This is the story of that expansion. It's a detective story where the only clue is the light that has been stretched, tired, and transformed by its impossible journey across the cosmos. We're going to follow that clue, from its discovery in the 20th century to the mind-bending reality of galaxies moving faster than light. We'll explore a modern crisis in cosmology known as the Hubble tension, a glitch in our models that suggests the universe is expanding faster than our best theories predict. We are going to unpack how light gets stretched like a cosmic rubber band, how that proves the universe is growing, and why Einstein's ultimate speed limit isn't actually being broken. And finally, we'll arrive at the frontier of science, where astronomers are grappling with the possibility that our entire model of the cosmos might be incomplete. This is the story of a race light can never win, because space itself keeps changing the rules. The messenger and the medium. To understand this cosmic race, we need to get to know our two main characters. The messenger, light, and the medium it travels through, spacetime. Their stories are completely tangled up with each other. Let's start with the messenger. Light. What is it? At its heart, light is a wave, an electromagnetic wave. Picture dropping a pebble into a still pond. Ripples spread out, each with a peak and a trough. The distance between one peak and the next is its wavelength. Light works a lot like that. It's a traveling disturbance in the universe's electromagnetic fields. But unlike ripples on a pond, it doesn't need anything to travel through. It can move through the total vacuum of empty space, a self-sustaining wave of energy. This wavelength is everything. It's light's ID card. It's what separates a ray of sunlight from a cancer-causing X-ray, or a radio signal carrying a broadcast from across the planet. At one end of the electromagnetic spectrum, you have incredibly short, high-energy wavelengths like gamma rays and X-rays. Then you have ultraviolet light, followed by the tiny sliver our eyes can see. Visible light, from violet to red. As the wavelengths get longer and the energy gets lower, we move into infrared, microwaves, and finally, the colossal wavelengths of radio waves, which can be as long as mountains. Every single particle of light has a specific wavelength that tells us what it is and how much energy it's carrying. And as we're about to see, that identity can be changed. Now, for the medium. The racetrack itself. For most of history, we thought of space as an empty, unchanging void. A black backdrop for the stars and planets. It was the stage, not an actor in the play. Then, in the early 20th century, Albert Einstein demolished that idea with his theory of general relativity. He showed that space and time are woven together into a single, four-dimensional fabric, spacetime. And this fabric isn't static. It's dynamic, flexible, and it responds to the matter and energy within it. The classic analogy is a bowling ball on a trampoline. The stretched rubber sheet is the fabric of spacetime. If you place a heavy bowling ball, say, the sun on the sheet, it creates a deep curve. Now, if you roll a marble earth nearby, it won't travel in a straight line. It follows the curve created by the bowling ball and falls into an orbit. This, Einstein said, is gravity. It's not a mysterious force pulling objects together. It is the actual geometry of spacetime, warped by mass and energy. Planets orbit the sun because they are following the straightest possible path through the curved spacetime the sun creates. This was a revolution. Space was no longer a passive box. It was a physical thing that could be bent and warped. And that insight is the key to everything that follows. If the fabric of spacetime can be curved by gravity, what else can it do? Can it be stretched? The answer, it turned out, was a huge yes. And this is where our two characters meet. What happens to a tiny photon of light when the very fabric of spacetime it's traveling through is being stretched? The journey isn't just getting longer in front of the photon, but behind it as well. The light is a messenger carrying a story, but the medium it travels through is actively rewriting that story before it ever arrives. The result is the single most important clue we have: the smoking gun that proves our universe is in a race with itself. The smoking gun. Cosmological redshift. In the early 1900s, the universe felt like a pretty cozy, static place. The Milky Way was basically the whole show, a vast island of stars in an infinite, quiet ocean. But there were a few weird smudges in the sky that didn't look like stars. Astronomers called them spiral nebulae, and nobody knew what they were. Were they gas clouds in our own galaxy, or were they distant, island universes, just like our Milky Way? An astronomer named Vesto Slipher started studying these nebulae in 1912. He was simply trying to analyze their light using a technique called spectroscopy, which spreads light out into its rainbow of constituent colors. Within this spectrum, you see dark lines, like a barcode. These are absorption lines, created when chemical elements in the object's atmosphere absorb light at very precise wavelengths. Every element has a unique, unchanging barcode. Slipher noticed something deeply strange. For most of these spiral nebulae, the entire barcode pattern was shifted towards the red end of the spectrum. He thought he knew what this meant. The Doppler effect. We hear it every day with sound. An approaching ambulance siren sounds high-pitched because the sound waves are compressed. As it speeds away, the siren sounds low-pitched because the waves are stretched out. Light does the same thing. An object moving towards us has its light waves compressed a blue shift. An object moving away has its light waves stretched a redshift. What Slipher saw was a clear redshift. These nebulae were moving away from us at incredible speeds, some over 1,000,000 miles per hour. This was amazing, but the real bombshell was still to come. Enter Edwin Hubble. With the new 100-inch Hooker telescope, the most powerful in the world, Hubble could see individual stars within these nebulae. He focused on a special type called a Cepheid variable. These stars pulsate at a rate that's directly linked to their true brightness. They're standard candles. If you know how bright something truly is and you measure how dim it appears, you can calculate its distance. Hubble used these stars to prove, once and for all, that these nebulae were other galaxies, millions of light years away. Then he combined his distance measurements with Slipher's redshift data. In 1929, he announced a discovery that would forever change our place in the cosmos. The farther away a galaxy was, the faster it was receding from us. This relationship, now known as Hubble's law, was the first hard evidence for an expanding universe. But the light wasn't just being Doppler shifted. The space between the galaxies was stretching, and it was stretching the light waves right along with it. This is what we now call cosmological redshift. Imagine two ants on a big rubber sheet. One ant shines a flashlight at the other. While the light is in transit, someone starts stretching the sheet. The light wave, like a ripple on the sheet's surface, gets stretched out along with the fabric it's on. Its wavelength gets longer. By the time it reaches the second ant, the light is redder. The further apart the ants are, the longer the light's journey, and the more the sheet stretches while it's traveling. So, greater distance means greater stretching, which means greater redshift. This is exactly what Hubble saw. The redshift of a distant galaxy is a direct measure of how much the universe has expanded since that light began its journey. We measure this with a number called z. A galaxy with a redshift of z equals 1 means its light was emitted when the universe was half its present size. The light's wavelength has literally been doubled by the expansion of space. Astronomers using the James Webb Space Telescope have found quasars with redshifts higher than z equals 7, and even some exceeding z equals 10. The light from an object at z equals 7 began its journey when the universe was only about 770 million years old, a fraction of its current age. Its light has been stretched by a factor of 8. Light that was emitted as brilliant ultraviolet radiation has been stretched so much that we detect it today as faint infrared. The ultimate example is the cosmic microwave background, CMB. This is the oldest light in the universe, the afterglow of the Big Bang itself. It was emitted when the universe was just 380,000 years old, a searingly hot, dense plasma. The light back then wasn't quite like the inside of a star, but it was intensely bright, mostly in the form of infrared radiation. In the 13.8 billion years since, the universe has expanded by a factor of about 100. That ancient light has been stretched by that same factor, all the way across the spectrum, until today it arrives on Earth as low-energy microwaves. When you see a map of the CMB, you are looking at the most redshifted, most stretched out light possible. It's the baby picture of the universe, and it is the smoking gun. The mind-bending twist: faster than light? So, the universe is expanding. The farther away a galaxy is, the faster it moves away. This leads to a question that seems to break physics. If recession speed is proportional to distance, is there a distance where a galaxy's speed equals and then exceeds the speed of light? The answer is yes. And here's where the cosmic race gets truly bizarre. Let's get the big rule out of the way, as laid down by Einstein. Nothing can travel through space faster than the speed of light. This is the cosmic speed limit. It's a fundamental property of cause and effect. If you could break it, you could send a signal that arrives before it was sent. The universe protects itself from this. As you accelerate something with mass closer and closer to light speed, it gets effectively more massive, requiring infinite energy to reach the limit. It's a hard wall. So, how can a galaxy recede from us faster than light? The key is one of the most important distinctions in all of cosmology. The galaxy isn't moving through space that fast. The space itself is expanding, carrying the galaxy along for the ride. Think of it like this. You have a long loaf of unbaked raisin bread dough. Pick 2 raisins 1 inch apart. Now, you put it in the oven. As the dough rises, it expands everywhere. After an hour, that 1 inch of dough between the raisins has become 3 inches. From the first raisin's point of view, the second raisin moved 2 inches away in an hour. Now, pick a third raisin that was 10 inches away. After that same hour, the 10 inches of dough between them has also tripled, becoming 30 inches. From the first raisin's perspective, this third raisin moved 20 inches in the same hour. It moved 10 times faster, simply because there was 10 times more dough in between to expand. The raisins didn't go anywhere in the dough. They were just carried apart as the dough itself rose. And if you had a raisin far enough away, all the expanding dough in between could easily carry it away faster than a tiny ant could crawl across the loaf. The ant's speed is the local speed limit, but the expansion of the dough itself has no limit. This is what's happening in our universe. Galaxies are the raisins. Spacetime is the dough. And the speed of light is the ant. A distant galaxy isn't moving in the normal sense. It's mostly sitting still in its local patch of space. But the vast gulf of space between that galaxy and us is expanding. This creates a conceptual boundary around us called the Hubble sphere. It marks the distance at which the universe's expansion speed equals the speed of light, currently at a radius of roughly 14 to 16 billion light-years. Any galaxy beyond the Hubble sphere is, right now, receding from us faster than light. The most distant galaxies we can observe are currently estimated to be about 46.5 billion light-years away, meaning they are receding from us at more than 3 times the speed of light. This solves one paradox, but it opens another. If a galaxy is moving away from us faster than light, how can we see it? How can the light from it ever reach us? The answer is that the light had a head start. The light we see today from a galaxy 46.5 billion light-years away didn't start from that far away. It began its journey billions of years ago when the universe was much smaller and that galaxy was much, much closer to us, well inside our Hubble sphere. When the light from that distant galaxy was first emitted, it was pointed our way and began traveling at speed c. The space between it and us was expanding, but because the galaxy was closer then, the expansion was slower than the speed of light. The light was fighting an uphill battle, like someone walking up a down escalator that's moving slower than they are. Over billions of years, the universe kept expanding. The galaxy that emitted the light was carried further away, eventually crossing the Hubble sphere. But the photon of light it sent out eons ago was still on its journey, still plugging away at speed c through whatever local space it was in. It had already covered a vast distance and was now much closer to us. Eventually, that photon crossed a threshold where it could finally close the remaining distance to Earth. So, we see the light today because it was sent when the race was still winnable. The galaxy itself is now superluminal, but the light we see is an ancient ghost from a time when it was not. The cosmic crisis, the Hubble tension. We know the universe is expanding. For decades, the big question for cosmologists has been, how fast? Pinning down this expansion rate, known as the Hubble constant, h0, is crucial. It helps us figure out the age, size, and ultimate fate of our universe. But in the 21st century, this quest has led to one of the biggest crises in science, the Hubble tension. Here's the problem. We have 2 completely different ways to measure the expansion rate, and they're giving us 2 different answers. The first method looks at the local universe around us today. It's the direct descendant of Hubble's original method. We find standard candles, objects with a known brightness like Cepheid variable stars and type Ia supernovae, and measure how dim they appear to calculate their distance. Then we measure their redshift to get their speed. Put it all together, and you get the expansion rate. After decades of painstaking work by teams like the SH0ES group, this method gives a very precise value. About *73 kilometers per second per megaparsec. This means for every 3.26 million light-years you look out into space, the universe is expanding an extra 73 kilometers per second faster. It's an incredible achievement. There's just one problem. The second method looks at the early universe, using the afterglow of the Big Bang, the cosmic microwave background, CMB. Satellites like the Planck mission have made incredibly detailed maps of the CMB, showing tiny temperature fluctuations from when the universe was just 380,000 years old. Cosmologists have a staggeringly successful model called the Lambda CDM model, Lambda CDM. It describes a universe made of roughly 5% normal matter, 27% dark matter, and 68% dark energy. This model perfectly explains the patterns in the CMB. By plugging the CMB data into this model, scientists can run the clock forward and predict how a universe that started like that should be expanding today. It's a prediction of what the Hubble constant ought to be. And here's the crisis. The prediction from the early universe doesn't match the measurement from the local universe. The value predicted by the Planck data and our standard model is about **67 kilometers per second per megaparsec. This is the Hubble tension, 73 versus 67. It might not seem like a huge difference, but the error bars on these measurements are now so small they don't overlap. The discrepancy is real. The universe appears to be expanding about 9% faster in our neighborhood than our best model of the early universe says it should be. It's like building a bridge from both sides of a canyon, using the most precise engineering possible, only to find when you get to the middle that the two ends don't meet. It tells you your blueprint, your fundamental understanding of the bridge is wrong. Something is missing from our cosmic blueprint. The suspects. What's causing the tension? When your best model of the universe breaks, it means one of two things. Your measurements are wrong, or your model is wrong. As evidence grows that the measurements are right, cosmologists are forced to wonder if the standard Lambda CDM model is incomplete. This has kicked off a thrilling hunt for new physics. Suspect 1. Deceptive dark energy. The lambda in the Lambda CDM model represents dark energy as a constant, unchanging force. But what if it's not constant? One idea is early dark energy. This theory suggests a new energy field briefly flared up after the Big Bang, giving the young universe an extra push. This would change the initial conditions and could tweak the prediction for the Hubble constant, bringing it into line with local measurements. Another, wilder idea is that dark energy is getting stronger over time, a concept known as phantom energy. That would lead to a terrifying, Big Rip finale for the universe. Suspect 2. A new flavor of dark matter. Our model assumes dark matter is cold and interacts only through gravity. But what if there's more to the dark sector? Some theories propose a new type of particle, maybe a form of dark radiation, that was buzzing around in the early universe. These extra particles would have added to the total energy, changing the expansion rate just enough to resolve the tension. Suspect 3. Gravity itself is flawed. This is the most radical idea. The whole model is built on Einstein's general relativity. It works perfectly in the solar system, but maybe it needs a tweak on the largest cosmic scales. A modified theory of gravity could potentially explain the universe's behavior without dark energy, or at least change the expansion history in a way that solves the puzzle. The latest plot twist. Just as the evidence seemed to point toward new physics making the universe expand faster, a shocking new possibility has emerged. Some controversial studies from late 2025 suggest that after correcting for how Type Ia supernovae behave in galaxies of different ages, the data might actually point to the universe's expansion slowing down today. This claim, which is still hotly debated, flies in the face of the Nobel Prize-winning discovery of acceleration. If confirmed, it wouldn't just challenge the standard model, it would detonate it, suggesting dark energy might be a force that weakens over time. We are living in a fascinating time where the foundational story of our universe is being questioned. The Hubble tension isn't just a number problem. It's a giant, flashing arrow pointing toward a deeper reality we have yet to uncover. The universe is telling us we've missed something huge. Whether it's evolving dark energy, a new particle, a flaw in gravity, or this wild new idea that the expansion is slowing down, the answer is out there, waiting in the light of distant stars. So, what do you think is the culprit? Let me know your theory in the comments below. We started with a simple idea, a race between light and the expanding universe. We followed that single ray of light across spacetime and saw how its journey stretches its very wavelength, turning it red, the definitive proof of an expanding cosmos. We navigated the paradox of galaxies receding faster than light without ever breaking Einstein's ultimate speed limit. And we ended up here, at the ragged edge of our knowledge, facing a crisis called the Hubble tension. This isn't just a small crack in our theory, it's a chasm between the universe as it was and the universe as it is. It tells us that the cosmos is more complex, more mysterious, and stranger than we ever imagined. The race that light can never win isn't a story about failure. It's a story of revelation. The tired, stretched-out light that finally reaches us is a message, proof that reality is a grand, unfolding drama. And we are just beginning to figure out the script. Scientists just overturned the end of the universe. For as long as we've been human, we've looked at the stars and wondered, where did this all come from? And maybe more importantly, how will it all end? For the last 25 years, we thought we had the answer to that second question. We had a story, a definitive one, about the ultimate fate of our universe. It was the story of a runaway cosmos, a universe expanding faster and faster, driven by a mysterious phantom-like force called dark energy. The narrative was set. Every galaxy, every star, would eventually be pulled so far apart that the cosmos would become an endless, cold, and lonely void. This was the big freeze. This was our accepted end. But what if that story is wrong? What if the phantom force isn't constant? Groundbreaking new evidence is hinting that the power of dark energy might be weakening. And if this is true, it doesn't just tweak the details, it forces us to completely reopen the book on the end of the universe. The reign of dark energy, a story of a runaway universe. To get why this new hint is so earth-shattering, we have to go back to 1998, a year that turned cosmology on its head. For most of the 20th century, the great cosmic debate was all about the breaks. Everyone knew the universe was expanding, thanks to Edwin Hubble. He saw galaxies moving away from us, like raisins in a baking loaf of bread. But the one force that runs the show on a cosmic scale is gravity. Gravity pulls things together, it builds stars, galaxies, and galaxy clusters. So, it made perfect sense that gravity should be acting as a cosmic brake, constantly pulling on the fabric of space-time and slowing the expansion down. The only real question was, how strong are the brakes? There were two main options. If there was enough stuff, enough matter, and therefore enough gravity, the expansion would eventually stop, reverse, and the whole universe would collapse in a fiery, big crunch, a mirror image of the Big Bang. If there wasn't enough matter, gravity would still slow things down, but not enough to stop the expansion completely. The universe would expand forever, just at a slower and slower rate. To find out which future was ours, two teams of astronomers set out to measure this slowdown. Their plan was brilliant. Use a special kind of exploding star, a type Ia supernova, as a standard candle. These supernovas are cosmic lighthouses because they all explode with almost the exact same brightness. If you know how bright something really is, you can tell how far away it is by how dim it looks. By finding these supernovas in distant galaxies and measuring their redshift, how much their light has been stretched as they speed away, the astronomers could map the universe's expansion history. They expected to see the expansion slowing. They found the exact opposite. The distant supernovas were even dimmer, and therefore farther away, than they should have been. This could only mean one thing. The expansion of the universe wasn't slowing down. It was speeding up. Imagine throwing a ball in the air and instead of falling, it rockets upward, faster and faster. That was the level of shock. The discovery was so profound it won the Nobel Prize in Physics in 2011. This gave birth to dark energy. It's just a name for whatever is causing this acceleration, acting like an anti-gravity that pushes spacetime itself apart. And here's the scary part. While gravity tries to pull everything together, dark energy pushes everything apart. About 6 billion years ago, the universe hit a tipping point. The push of dark energy became stronger than the pull of gravity. The cosmic brakes didn't just fail. The universe slammed its foot on the accelerator. This led to our standard model of cosmology, called lambda CDM. Lambda stands for the cosmological constant, our term for dark energy, and CDM for cold dark matter. This model has been a huge success, but it paints a bleak picture of the end, the big freeze. In this future, the accelerating expansion tears everything apart until our own galaxy is an isolated island in an endless, empty void. Stars burn out, black holes evaporate, and the universe becomes a cold, featureless soup approaching absolute zero. For over 20 years, this has been the accepted story of our end. The first cracks in the foundation, the Hubble tension. The lambda CDM model was a triumph, but in science, nothing is ever truly settled. Over the last decade, some serious cracks have appeared in the story. The biggest one is a problem called the Hubble tension. Simply put, the Hubble tension is a major disagreement about how fast the universe is expanding today. The two main ways we measure this number give us two different answers. The first method looks at the early universe by studying the cosmic microwave background, CMB, the afterglow of the Big Bang. Satellites like Planck have mapped this ancient light, and by plugging that data into our lambda CDM model, we can predict what the expansion rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. The second method looks at the late universe around us. Using tools like Type Ia supernovae, our standard candles, we can directly measure the expansion happening now. This method gives a higher value, around 73 or 74 kilometers per second, MPC. That difference might not sound like much, but for cosmologists, it's a 5-alarm fire. The measurements are so precise now that they are statistically incompatible. They can't both be right. The disagreement has hit a 5 sigma level of significance, which in physics is the gold standard for a discovery. It's a huge clue that our standard model, lambda CDM, is either wrong or incomplete. The Hubble tension was the first major sign that our story about the cosmos was missing a key ingredient. And it was pointing toward a much bigger surprise. The hint that shook cosmology. For years, the Hubble tension was a nagging puzzle. But the idea of an accelerating universe held firm. Then, starting in late 2024 and through 2025, new data began arriving from the Dark Energy Spectroscopic Instrument, or DESI. DESI is a marvel, a collection of 5,000 robotic eyes on a telescope in Arizona that can map 5,000 galaxies every 20 minutes. Its mission is to create the most detailed 3D map of the universe ever, charting tens of millions of galaxies going back 11 billion years. DESI uses a different kind of cosmic ruler, baryon acoustic oscillations, or BAO. These are faint, frozen ripples in the distribution of galaxies left over from sound waves in the very early universe. These ripples have a standard size, about 500 million light-years across. By measuring how big this ruler appears at different times in cosmic history, Dacey can track the expansion of the universe with incredible precision. In a series of papers, the Dacey collaboration released its first big analysis. On its own, the Dacey data was consistent with the standard lambda CDM model. But then, they combined their data with other cosmic measurements, like those from the CMB and supernova surveys. And that's when a startling picture emerged. The combined data hinted that dark energy might not be constant. It might be evolving and, more specifically, weakening over time. Let's be very clear. This is not a definitive discovery. The gold standard for a discovery in physics is 5 sigma, a statistical level meaning there's less than a 1 in a million chance the result is a fluke. The hint of evolving dark energy is currently between 2, 8 and 4, 2 sigma. That's significant. It's a flashing yellow light on the dashboard of cosmology, but it's not proof. Many 3 sigma hints have disappeared with more data. But this hint is incredibly tantalizing. It suggests the force pulling our universe apart isn't a static feature of space, but a dynamic entity that changes. Further analyses from the Separate Dark Energy Survey, DE, added complexity. While its final 6-year data still aligned best with the standard lambda CDM model, it also found that models with evolving dark energy fit the observations well. What all this means is that the simple story of a runaway universe might be wrong. After billions of years of flooring the cosmic accelerator, dark energy might be losing its punch. And if that's true, our destiny is no longer written in stone. A universe with a new destiny? If these hints from Dacey are confirmed, if dark energy is weakening, then the future of the universe is completely rewritten. The cosmic tug-of-war we thought was over is suddenly back on. If dark energy's strength is fading, gravity's pull will slowly start to matter more. The acceleration would stop, and the expansion would begin to slow down. This opens the door to a fate that was largely dismissed after 1998, the Big Crunch. In this scenario, if dark energy keeps weakening, gravity eventually wins. The expansion of the universe slows to a halt and then reverses. Galaxies would stop moving away and start rushing toward us. The universe would contract, getting hotter and denser until all matter is ripped apart into a primordial plasma, collapsing into a singularity much like the state from which it all began. This leads to an even more mind-bending idea, the Big Bounce. Some quantum gravity theories suggest a universe can't collapse to an infinite point. Instead, quantum forces would halt the collapse and cause the universe to bounce back out in a new Big Bang, creating a new cosmos from the ashes of the old one. This idea of a cyclic universe, which was sidelined by the discovery of acceleration, is suddenly a viable contender again. The main point is that the game has changed. For 2 decades, our fate seemed sealed in a big freeze. Now, the book is wide open. The Big Crunch and Big Bounce are no longer just historical footnotes. They're back on the table, revived by these stunning new possibilities. The ultimate fate of everything is once again one of the biggest unanswered questions in science. This is science happening as we speak. We are watching a potential revolution in our understanding of the cosmos, unfolding as new data comes in. The story isn't over. It feels like we've just hit the biggest plot twist imaginable. If you want to follow this journey into the cosmic unknown, make sure to subscribe and follow along. You'll be the first to know as we continue to unravel this grand mystery together. The grand cosmic mystery. So, where does this all leave us? The honest answer is, we don't know for sure. We haven't overturned the end of the universe, but the foundations of our understanding have been profoundly shaken. We are seeing the scientific process at its most thrilling. The standard model that has served us for decades is facing its most serious challenge yet. There's the undeniable Hubble tension, telling us for years our picture is incomplete. And now we have these direct hints from Daisy that the lambda part of lambda CDM, the constant dark energy, might not be constant at all. As Dr. Seshadri Nadather of the University of Portsmouth put it, it's not just that the data continues to show a preference for evolving dark energy, but that the evidence is stronger now than it was. These two problems might even be connected. A version of dark energy that changes over time could potentially resolve the Hubble tension by reconciling the measurements from the early and late universe. The pieces are just starting to come together. Over the next few years, Daisy will complete its full survey, giving us much more data. The Vera C. Rubin Observatory will also provide an even deeper view. These observatories will either confirm these hints and trigger a paradigm shift, or they will fade away, leaving us with an even deeper mystery. One thing is certain. Our simple story of the universe's end is no longer enough. We thought we were speeding toward a cold, lonely finish line. Now, it seems the final chapter has yet to be written. The universe, it turns out, is still full of surprises. For 25 years, the story of dark energy was simple, elegant, and terrifying. It was a constant, unchanging force pushing our universe toward a desolate end. But the cosmos is rarely that simple. The latest evidence suggests a more complex, more dynamic, and ultimately more mysterious reality. The phantom force might be changing, weakening, and rewriting our destiny. We've been forced to look beyond the big freeze and reconsider futures we once thought impossible. A fiery big crunch or an eternal big bounce. We are on the edge of a new era in cosmology, where our most fundamental theories are being tested like never before. The end of the universe is once again an unsolved mystery. So what do you think? Are we destined for a freeze, a crunch, a bounce, or something we haven't even imagined yet? Let me know your thoughts in the comments below. Did we just break the universe's speed limit? For more than 100 years, there's been one unbreakable rule in physics. Nothing goes faster than the speed of light. It's the ultimate speed limit for the entire universe, a law woven right into the fabric of reality. But what if I told you the universe itself breaks that rule every single second? What if galaxies, billions of light years away, are flying away from us faster than light? And what if the very scientists who discovered this are now saying their own measurements are wrong, throwing our understanding of everything into chaos? We've known the universe is expanding, but it seems to be expanding way too fast, and it's tearing a hole in our most fundamental theories. So, did we just break the universe's speed limit? The answer is complicated. And it's way more fascinating than you can imagine. It's a story that challenges not just our place in the cosmos, but the very nature of space and time. And by the end of this, you'll see the universe in a whole new light. The foundations of an expanding universe. To really get this cosmic mystery, we need to jump back in time to the early 20th century. It all starts with a mind that needs no introduction. Albert Einstein. In 1915, he published his theory of general relativity, this revolutionary idea that gravity isn't a force, but a curve in spacetime made by mass and energy. But when Einstein used his beautiful equations on the whole universe, he found something that really bothered him. His math showed that the universe had to be either expanding or contracting. It couldn't just sit still. This idea of a changing, evolving cosmos went against everything scientists and philosophers believed at the time. Everyone just assumed the universe was eternal and unchanging. So, to make his math fit this perfect, static universe, Einstein tossed in a new term, a fudge factor that he called the cosmological constant. He pictured it as a kind of anti-gravity, an energy built into space itself that would push everything apart just enough to cancel out gravity's pull, keeping the universe perfectly balanced. But while Einstein was trying to hold the universe still, other brilliant minds were letting it go. A Russian physicist named Alexander Friedmann and, completely separately, a Belgian priest and astronomer named Georges Lemaitre just trusted Einstein's equations. They didn't add a fudge factor. They followed the math where it led, and it led them to the exact same, shocking conclusion. The universe has to be expanding. Lemaitre even took it a step further, suggesting that if it's expanding, it must have had a beginning, a day without yesterday, a single point of creation from a primeval atom. It was an idea that would eventually grow into the Big Bang theory. Now, these were just theories on a chalkboard. The real proof had to come from space itself, and from a man whose name would become legendary, Edwin Hubble. Working at the Mount Wilson Observatory in the 1920s, Hubble was using the world's most powerful telescope to look at these fuzzy blobs in the sky they called spiral nebulae. The big debate was whether these were just gas clouds inside our own Milky Way, or entire island universes. Galaxies, just like ours, but incredibly far away. Hubble settled that debate for good. He found a special kind of star in the Andromeda Nebula called a Cepheid variable. These stars are like cosmic lighthouses. They pulse, getting brighter and dimmer at a regular rhythm. Thanks to an earlier discovery by astronomer Henrietta Swan Leavitt, it was known that the slower a Cepheid pulsates, the brighter it truly is. So, by timing a Cepheid's pulse, Hubble could figure out its real brightness. Then he could compare that to how bright it looked from Earth and calculate its distance, just like you judge the distance of a car's headlights on a dark road. His result was stunning. Andromeda was almost 1,000,000 light-years away, way outside the Milky Way. It was another galaxy. But that was just the start. As Hubble measured more and more galaxies, he also studied their light. He took their light and passed it through a prism, splitting it into a rainbow of colors called a spectrum. And he noticed something weird. The light from distant galaxies was almost always shifted toward the red end of the spectrum. This is called redshift. You hear a version of this every day with the Doppler effect. Think of an ambulance siren. As it races toward you, the sound waves get squished, making the pitch higher. As it speeds away, the waves get stretched, and the pitch gets lower. Light does the same thing. If something's moving toward us, its light waves get squished toward the blue end of the spectrum, that's blue shift. If it's moving away, the waves get stretched toward the red end, redshift. Hubble saw that almost every galaxy was redshifted. They were all moving away from us. But the most incredible part was when he graphed their speed versus their distance. He found a straight line. The farther away a galaxy is, the faster it's moving away. This became known as Hubble's law. This was the proof. It was exactly what Friedmann and Lemaitre had predicted. The universe was expanding. When Einstein visited Hubble and saw the evidence, he famously called his cosmological constant his greatest blunder. The universe wasn't static, it was growing. The speed of this expansion is captured by one critical number. The Hubble constant, or h0. It tells us how fast the universe is expanding per unit of distance. The units are a little strange: kilometers per second per megaparsec. A megaparsec is a massive distance, about 3.26 million light-years. So, a Hubble constant of, say, 70 kilometers per second per megaparsec means that for every megaparsec farther out you look, a galaxy appears to be moving away 70 kilometers per second faster. Now, let me be clear. This wasn't an explosion in space. It was an expansion of space itself. The best analogy is a loaf of raisin bread rising in an oven. The raisins are galaxies, and the dough is space. As the dough expands, all the raisins get farther apart. From any one raisin's point of view, all the other raisins are moving away. And a raisin that's twice as far will seem to move away twice as fast, simply because there's twice as much expanding dough in between. That's Hubble's law. We're not at the center. An observer in any galaxy would see the exact same thing. This is the picture of our universe we've had for almost a century. A cosmos born in a Big Bang, expanding and cooling ever since. The speed limit and a cosmic clarification. So, back to the big question. Did we break the universe's speed limit? If galaxies farther away are receding faster, does that mean that somewhere, way out there, a galaxy is moving away from us faster than light? The answer is a definitive, and pretty mind-bending, yes. And the next question is obvious. Doesn't that totally violate Einstein's theory of relativity? The answer to that is an equally mind-bending, no. To get why, we need to separate two of Einstein's ideas. First, there's special relativity from 1905. That's the one that gave us E=mc² and the cosmic speed limit. It says no object, no information, no anything can travel through space faster than light. This law is absolute. It protects cause and effect. If you could send a signal faster than light, you could break reality and send messages into the past. But notice the key phrase: through space. Special relativity is a local law. It governs things moving within the stage of spacetime. When we're talking about the whole universe, where space itself is expanding, we need to use Einstein's masterpiece, general relativity. General relativity tells us space isn't just a static background, it's a dynamic thing. It can bend, it can warp, and as Hubble found, it can expand. And here's the solution to our paradox. The cosmic speed limit applies to things moving through space, not to the expansion of space itself. Let's go back to the raisin bread. Special relativity says no raisin can decide to zip through the dough faster than the speed of light. But general relativity puts no speed limit on how fast the asterisk dough itself can expand. The expansion rate is a speed per distance. If the value is around 70 kilometers per second per megaparsec, we can do the math. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. If you keep going out, you'll eventually reach a distance where the total expansion of space between you and a distant galaxy adds up to more than 300,000 kilometers per second, the speed of light. This boundary is called the Hubble horizon, and it's about 14 billion light-years away. Any galaxy beyond that horizon is receding from us faster than light. In fact, the most distant galaxy we can see right now is actually over 30 billion light-years away today because of all the expansion that's happened, and it's zipping away from us at speeds much, much faster than light. Again, this breaks no laws. That galaxy isn't moving in the normal sense. It's just sitting there in its own patch of space. It's the space between us and it that's expanding like crazy. No information is being sent faster than light. Actually, it's the opposite. A beam of light shot from that galaxy toward us today would get swept backward by the expanding space and would never reach us. Those galaxies have passed a cosmic point of no return. We can see the ancient light they emitted billions of years ago, but their present is forever cut off from us. So, saying a galaxy is moving away is kind of a misleading shorthand. A better way to think of it is two ants on a rubber band that's being stretched. Neither ant can run faster than its own top speed, but the distance between them can grow faster than that if you stretch the rubber band fast enough. That's our universe. The crisis. Introducing the Hubble tension. For decades, this picture of an expanding universe has been the foundation of our standard model of cosmology, known as lambda CDM. Lambda is the cosmological constant, brought back to life as the mysterious, dark energy that's making the expansion speed up. CDM stands for cold dark matter, the invisible stuff whose gravity holds galaxies together. This model has been a huge success, explaining almost everything we see with just 6 numbers. One of the most important of those numbers is the Hubble constant, h0. Nailing down its exact value has been a top goal for a century. It's not just a number, it tells us the age, size, and fate of our universe. A higher number means a faster expansion in a younger universe. For years, scientists got slightly different results when they measured it, but the error bars were big enough that everyone figured they'd eventually agree. But they didn't. As our tools got more precise, the measurements got stuck in two different camps, with error bars so small they don't overlap at all. This disagreement is the Hubble tension. And in cosmology, it's a full-blown crisis. So, let's meet the two teams. In one corner, we have the early universe team. They look at the oldest light in the universe, the cosmic microwave background, or CMB. This is the afterglow of the Big Bang. About 380,000 years after the start, the universe cooled down enough for atoms to form, and light that had been trapped in a hot soup of plasma was finally set free. Today, that light has been stretched into microwaves, and it fills the entire sky. Satellites like the European Space Agency's Planck have mapped it in stunning detail. This baby picture of the universe isn't perfectly smooth. It has tiny hot and cold spots, ripples that were the seeds of all galaxies. By studying the size of these spots, and using the trusted lambda CDM model, scientists can predict how the universe should have expanded since then. They can run the clock forward and calculate what the expansion rate should be today. The result from the incredibly precise Planck data is a Hubble constant of about 67.4 kilometers per second per megaparsec. In the other corner is the late universe team. They don't predict the expansion rate, they measure it directly, right here and now. The most famous project is called SH0ES, led by Nobel laureate Adam Rees. Their method is the cosmic distance ladder. It's a series of steps to measure farther and farther into space. The first rung is simple geometry. As the Earth orbits the Sun, nearby stars appear to shift slightly. By measuring that shift, we can calculate their distance with trigonometry. The second rung uses those known distances to calibrate our cosmic lighthouses, the Cepheid variable stars. The third and final rung uses those Cepheids to calibrate an even brighter beacon, type Ia supernovae. These are exploding stars that all reach the same peak brightness, making them perfect, standard candles, to measure distances billions of light years away. By measuring the distance to these faraway supernovae and then measuring their redshift, the SH0ES team calculates the Hubble constant directly. After years of work with the Hubble Space Telescope and new confirmations from the James Webb Space Telescope, their result is solid. They consistently measure a value of about 73 kilometers per second per megaparsec. And there it is. The Hubble tension. 67.4 versus 73. That might not sound like a lot, but for modern cosmology, it's a canyon. The error bars are so small now that the two values are in what's called a 5 sigma tension. That means there's only a 1 in 3.5 million chance this is a random fluke. To put it another way, someone, or something, is wrong. What could be causing the tension? Exploring the implications. So, what gives? This is where we move from known science into the thrilling frontier of research. The Hubble tension is one of the biggest puzzles in physics today. Let's start with the most boring possibility first. Maybe someone just messed up the measurements. For years, people suspected the late universe team. The distance ladder is tricky. An error on one rung messes up all the others. But the James Webb Space Telescope, with its incredible infrared vision, has double-checked the measurements and found that the Hubble telescope was right all along. With measurement errors looking less and less likely, as Adam Rees said, what remains is the real and exciting possibility that we have misunderstood the universe. Okay, so what about the early universe team? The physics of the CMB is solid, but maybe the lambda CDM model we use to connect the past to the present is flawed. Well, other experiments have confirmed the Planck measurement, so that side seems pretty robust too. Scientists are also inventing brand new ways to measure the expansion, like using the gravitational waves from colliding neutron stars, but so far, they haven't settled the debate. This forces us into the most exciting possibility. We need new physics. Our standard model of cosmology must be missing something. The bridge between the early and late universe is broken. There are a few leading ideas for what's going on. One is that dark energy is more complicated than we thought. Maybe it isn't a constant, but has changed its strength over time. A blast of early dark energy could have sped up the universe's youth, which would throw off the predictions from the CMB. Another idea is that there are new, undiscovered particles from the early universe, a kind of dark radiation that would have changed the expansion history in a way our current model doesn't account for. Or, and this is the most radical idea, maybe Einstein's theory of general relativity itself needs a tweak on cosmic scales. Most physicists are hesitant to go there, but with a crisis this big, nothing is off the table. We are at a major crossroads in cosmology. This tension isn't just a number, it's a clue. It's a crack in our standard model, and through that crack, we might be about to see a much deeper reality. Back to the speed limit, the future. So how does this crisis affect galaxies moving faster than light? It doesn't change the basic idea, but it does turn up the volume. Faster than light recession is a direct result of expanding space, and that's true no matter what the exact value of the Hubble constant is. But, if the late universe team is right and the expansion is faster, at 73 kilometers per second, MPC, it means the universe is growing even faster than our standard model predicts. That means the Hubble horizon, the edge beyond which galaxies are lost to us forever, is a little bit closer. It means more galaxies are crossing that point of no return every year, their light vanishing from our future sky. It paints a picture of a more dynamic, and maybe lonelier, cosmos. The good news is, we are in a golden age of cosmology. We have incredible new tools to solve this mystery. The James Webb Space Telescope is already giving us a clearer view of the distance ladder. The European Space Agency's Euclid telescope is currently building a gigantic 3D map of billions of galaxies to trace the history of expansion. And on the ground, the Vera C. Rubin Observatory in Chile has just roared to life. In late February 2026, it issued its first science alerts, spotting hundreds of thousands of cosmic events in a single night. It's now beginning a decade-long mission to create a massive movie of the southern sky, discovering millions of supernovae that will let us measure the Hubble constant with stunning new accuracy. These instruments are our best hope. They will either find the mistake, or they will prove that our understanding of the universe is incomplete and point us toward a new kind of physics. We started with a simple question: did we break the universe's speed limit? And we learned that, yeah, in a way, the universe does it all the time. The fabric of space itself is expanding, carrying galaxies away from us at impossible speeds without breaking a single law of physics. But in chasing that answer, we found a much deeper mystery. We're in the middle of a crisis, where our two best ways of measuring the universe don't agree. We know it's expanding, but we can't agree on how fast. But this isn't a failure. This is exactly how science is supposed to work. This is what progress looks like. This tension is a clue, a breadcrumb trail left by the universe, pointing toward a deeper truth. It could unravel the secret of dark energy, reveal new particles, or even force us to rewrite the laws of gravity. We're on a tiny planet, looking out at everything, trying to piece together the whole story. And right now, we've hit a chapter with a missing page. The search for that page is going to be one of the most exciting scientific adventures of our time. The universe, it turns out, is still full of surprises. If you enjoyed this trip to the edge of what we know, be sure to hit that like button and subscribe for more deep dives into the cosmos. I really want to know what you think. What's causing the Hubble tension? Is it a tiny error we still haven't found, or are we about to discover brand new physics? Let me know down in the comments. The silent thing that's outrunning the speed of light. What if I told you the fastest thing in the universe is nothing? Not a particle. Not a wave. Not some souped-up starship. But the silent, empty, cold vacuum of space itself. An expanding void that's outrunning the most fundamental speed limit in all of physics. This isn't a what if. It's happening right now, all around you. The empty space between galaxies is stretching, pulling the cosmos apart at speeds that defy our everyday logic. And this paradox, this cosmic rule-breaking, holds a profound secret about the very fabric of the universe. It hints that the permanence we take for granted, the stars in the sky, the galaxies in our telescopes, is all just a fleeting illusion. We're living in a universe that is quietly and relentlessly erasing itself from our view. To understand how and why, we have to become cosmic detectives. And our first stop is the very law that this nothing seems to be breaking. The ultimate speed limit. Picture it. Galaxies racing away from us at twice the speed of light. Physics says that's impossible. And yet, it's a documented reality of our cosmos. So how can the universe cheat its own rules? The answer isn't in what's moving, but in the very fabric of reality that everything is moving through. The law of the cosmos, the foundation. Before we can really grasp this cosmic crime, we have to understand the law. It's a rule so fundamental, it's woven into the DNA of modern physics. Nothing can travel faster than the speed of light. This isn't just a friendly suggestion, it's a cornerstone of Albert Einstein's theory of special relativity. But what does it really mean? Why this specific speed, 299, 792, 458 meters per second in a vacuum, and not a little faster? The speed of light, see, isn't just about how fast a photon can move. It's the speed of causality itself. It's the absolute max at which any information, any cause and effect, can travel through the universe. If you could send a signal faster than light, you could theoretically send a message into your own past. You could know an event's outcome before it even happens. The entire logical structure of reality, where causes always come before effects, would crumble. Think of it as the universe's ultimate traffic law. This speed limit applies to anything with mass moving through spacetime. As you accelerate something with mass, its energy goes up. As it gets closer and closer to the speed of light, its relativistic mass skyrockets, demanding more and more energy to push it any faster. To actually reach the speed of light would take an infinite amount of energy, an impossibility for anything with a single atom of mass. That's why, for over a century, the speed of light has been the unbreakable speed limit. It's a barrier built right into the math of our universe. From the tiniest particle to the grandest starship, everything has to play by this rule. It dictates that if you're here, you can't instantaneously be over there. It takes time for your influence, your signal, your presence to cross space. And the fastest that journey can ever be is at speed c. So, when astronomers started seeing evidence of something that appeared to be smashing this sacred law, it wasn't just a curiosity. It was a crisis. And it was a clue that our understanding of the cosmos was profoundly incomplete, a clue that would lead us from a static, comfortable universe to one that is dynamic, violent, and far stranger than anyone had ever imagined. The investigation began not by looking at the law itself, but by staring into the vast darkness between the stars. The first clue, the investigation begins. Our story now jumps to the early 20th century. Back then, our own Milky Way galaxy was pretty much it, the whole universe. Those faint, fuzzy patches of light we saw in telescopes, called spiral nebulae, were just thought to be swirling gas clouds inside our own cosmic city. The universe felt static, eternal, and comfortably small. But a revolution was brewing, led by a man who would completely redraw our map of reality: Edwin Hubble. Working at the Mount Wilson Observatory in California with the most powerful telescope on Earth, Hubble set out to measure the distances to these mysterious nebulae. His first huge break came from the work of another brilliant astronomer, Henrietta Swan Leavitt. Leavitt had discovered a special type of star called a Cepheid variable. These stars have a magical property. Their brightness pulses at a rate that's directly linked to their true, intrinsic luminosity. They're what astronomers call standard candles. If you know how bright something really is, you can figure out how far away it is just by seeing how dim it looks. In 1923, Hubble spotted a Cepheid variable star inside the Great Andromeda Nebula. Using Leavitt's method, he calculated its distance. The number he got was staggering, nearly 1,000,000 light-years away. This was ridiculously larger than even the wildest estimates for the size of the Milky Way. The conclusion was inescapable and universe-shattering. Andromeda wasn't a gas cloud in our galaxy. It was an asterisk entire galaxy in its own right, an island universe, with billions of its own stars. In one fell swoop, the known universe went from one galaxy to countless. Humanity was suddenly much, much smaller. But that was just the beginning. Hubble and his assistant, Milton Humason, kept observing these new galaxies. As they did, they built on the work of another astronomer, Vesto Slipher. A decade earlier, Slipher had been analyzing the light from these nebulae and noticed something odd. When you pass light through a prism, it splits into a rainbow spectrum, marked by dark lines that act like fingerprints for chemical elements. Slipher saw that the light from almost every nebula he looked at was redshifted. Their spectral lines were shifted toward the red end of the spectrum. This is the cosmic version of the Doppler effect, like how an ambulance siren's pitch drops as it speeds away from you. A redshift in light meant these galaxies were moving away from us. Hubble's genius was connecting the dots. He took his distance measurements and compared them to Slipher's redshift measurements. What he found in 1929 was a stunningly simple and profound pattern. The farther away a galaxy was, the faster it was moving away from us. This wasn't random. It was an organized, predictable pattern. The universe wasn't static, it was expanding. This relationship, now known as the Hubble-Lemaitre law, was the first concrete clue in our cosmic detective story. It meant the universe wasn't some eternal stage, but a dynamic thing with a history. It implied that if you ran the clock backward, everything would rush together to a single, unimaginably dense point, an idea that would later get a name: the Big Bang. Hubble's discovery was a triumph. But hidden in his own data was a paradox he couldn't have seen coming. The very law he discovered, when pushed to its limits, would lead to a conclusion that seemed to break physics itself. It would lead to the reveal of something moving faster than light. The paradox revealed the aha moment. This is where our detective story takes a sharp, counterintuitive turn. Hubble's law is simple. A galaxy's recession speed is just a constant number, the Hubble constant, times its distance from us. The farther away it is, the faster it recedes. But what happens when that distance gets truly, mind-bogglingly vast? Let's use the old raisin bread analogy. Imagine galaxies or raisins scattered in the dough of spacetime. As the dough bakes and expands, all the raisins move farther apart. A raisin near you moves away slowly. A raisin twice as far away moves away twice as fast, because there's twice as much expanding dough between you and it. A raisin on the far side of the loaf is moving away the fastest of all. Crucially, the raisins themselves aren't actually moving through the dough. They're being carried along by the expansion of the dough itself. This is the key to the whole paradox. When we see distant galaxies receding from us, they aren't firing up rocket engines and blasting through space. The galaxies themselves might be lazily drifting in their own local neighborhood. The incredible speed we see is an effect of the expansion of space itself. It's the fabric of spacetime between us and that distant galaxy that is stretching. And here's the aha moment. Einstein's speed limit, the speed of light, applies to the motion of objects through space. It does not apply to the expansion of space. Spacetime itself can do whatever it wants. This means that if you look far enough out into the cosmos, there will be a point where the cumulative effect of all the expanding space between you and a distant galaxy adds up to a recession speed faster than the speed of light. This isn't just a theory. Based on current measurements of the Hubble constant around 73 kilometers per second per megaparsec for the local universe, this line is crossed at a distance of about 14 billion light-years. Any galaxy beyond that distance is receding from us, right now, faster than 299, 792, 458 meters per second. We can see galaxies that are currently over 30 billion light-years away. Simple math tells us their recession speed is more than double the speed of light. So, how can we see them? How can the light from something that's outrunning its own light possibly reach us? The solution is another layer to this puzzle. When the light from that galaxy started its journey towards us billions of years ago, the galaxy was much, much closer. Back then, it was well within that 14 billion light-year boundary. Its light was able to make progress towards us, outrunning the expansion of space in its local region. But as that little photon traveled across the cosmos, the space it was crossing continued to expand, both behind it and in front of it. The journey kept getting longer. By the time that ancient photon finally hits our telescopes, the galaxy that sent it has been carried by cosmic expansion to a place so far away, it's now receding from us at superluminal speed. We are seeing a ghost, an image of the galaxy as it was, when it was younger and closer. The galaxy as it exists right now is moving away so fast that any light it emits today will never reach us. This isn't a trick. It's a fundamental feature of our reality. The universe isn't a fixed arena. It's a dynamic, growing, stretching entity. And this stretching, this silent, relentless expansion of nothingness, is the fastest thing there is. It doesn't break Einstein's law. It just sidesteps it, revealing a deeper, stranger reality. But this revelation is just the beginning. The real secret isn't just that the universe is expanding. It's what this expansion is doing to our future. The secret of the void, the deeper mystery. Understanding that space itself can outrun light is one thing. But this fact unlocks even more profound mysteries that challenge our whole concept of permanence. This is where we uncover the deeper secret. The structure of our universe isn't fixed, and what we can see of it is constantly changing. Part A. The cosmic horizon. We all get the idea of a horizon on Earth. It's a line we can see up to, but not beyond. Our universe has horizons, too, but they're way more complex and consequential. In fact, it has two. The first is the asterisk particle horizon. This is the edge of the asterisk observable universe. Since the universe is about 13,787 billion years old, there's a maximum distance from which light has had time to reach us. Anything beyond this boundary is invisible, not because it's faint, but because its light, even traveling at top speed since the dawn of time, simply hasn't reached us yet. This defines everything we can possibly see. A sphere around us with a radius of about 46.6 billion light-years. But there's a second, more chilling boundary. The asterisk cosmic event horizon. This isn't a boundary in the past, but one in the future. Because of the accelerating expansion of space, there is a point of no return. Galaxies beyond a certain distance, currently around 16 billion light-years, are receding so fast that even though we can see their ancient light now, any light they emit today will never, ever reach us. The space between us and them is expanding faster than the light can cross it. Think about what that means. A galaxy can be right there in our sky, a beautiful spiral we can photograph, but in a very real sense, it's already gone. It has crossed our cosmic event horizon. For us, its story is over. We'll keep seeing its old light for trillions of years, getting more and more redshifted and frozen in time, but we will never know what's happening there now. The expansion of space has erased it from our future. This silent stretching of the void acts like a one-way door, letting old light in but allowing no new information out. Part B. The ghost in the machine, dark energy. For the first several billion years after the Big Bang, the universe's expansion was actually slowing down, held in check by the gravity of all the matter inside it. But then, about 5 to 6 billion years ago, something flipped. The expansion started to speed up. This was the landmark, Nobel Prize-winning discovery in 1998 that turned cosmology upside down. There had to be some mysterious, repulsive force pushing the universe apart, overwhelming gravity on the largest scales. This force was given a name as enigmatic as its nature: dark energy. Dark energy is now thought to make up about 70% of the entire universe. It's the engine driving this accelerated expansion. It's the ghost in the machine, ensuring those distant galaxies cross our event horizon and vanish from our future. But what is it? The leading theory is that it's the asterisk cosmological constant asterisk, an idea Einstein himself came up with and later called his biggest blunder. He first put it in his equations to make the universe static, but the idea has made a comeback. In this view, dark energy is just a property of space itself. It's the energy of the vacuum, and as space expands, more of this energy appears, pushing everything apart even faster. But there's another, more exotic idea: quintessence. Unlike a constant, quintessence would be a dynamic energy field that could change over time. Its strength could be evolving, maybe even weakening or growing. Some theories even paint it as a fifth fundamental force of nature. This isn't just academic. The nature of dark energy dictates the ultimate fate of everything. Part C. The Hubble tension, a cosmic crisis. The plot thickens with one of the biggest crises in modern cosmology: the asterisk Hubble tension. Simply put, we have two main ways of measuring the universe's expansion rate, and they give us two different answers. The first method looks at the late universe. It uses tools like Cepheid variables and exploding stars in nearby galaxies, the same kinds of methods Hubble pioneered. This approach consistently lands on a value of around 73 kilometers per second per megaparsec. The second method looks at the early universe. It studies the cosmic microwave background, CMB, the faint afterglow of the Big Bang, and uses our standard model of cosmology to predict what the expansion rate should be today. This method consistently gives a lower value, around 67. This disagreement, while it sounds small, is a huge deal and has resisted every attempt to fix it. It means either our measurements are flawed, or our entire standard model of the universe is incomplete. This tension has forced scientists to question everything. Does dark energy behave in ways we don't expect? Recent analyses from projects like the Dark Energy Spectroscopic Instrument, DESI, have added fuel to the fire, showing hints that dark energy may not be constant, but could be evolving over time. Some controversial studies, trying to correct for biases in supernova data, have even proposed the shocking idea that the acceleration might already be slowing down. The debate is raging. Is the universe speeding up toward a cold, empty future, or is something else going on? This crisis shows that the deeper we look, the more we realize how little we know. The silent thing outrunning light isn't just a curiosity. It's a clue pointing to a fundamental secret about cosmic evolution that we are only just beginning to grasp: the illusion of permanence, implications, and future. This brings us to the ultimate takeaway from our cosmic detective story. The faster-than-light expansion, driven by a mysterious dark energy whose true nature is fiercely debated, reveals a profound truth: the permanence of the cosmos is an illusion. The universe isn't a static museum of galaxies, but a living, breathing entity that is actively rewriting its own future. On one hand, gravity pulls matter together. It formed you, our planet, our solar system, and our Milky Way. In fact, the gravitational pull within our local group of galaxies is strong enough to beat the expansion. The Andromeda Galaxy is actually on a collision course with us. Stability is a local affair. But on the grandest scales, the silent expansion wins. It's an unstoppable force tearing the cosmic web apart. The galaxies we see are just fleeting snapshots. In 100 billion years, the expansion will have pushed all but our closest galactic neighbors beyond our cosmic event horizon. The night sky for a future civilization in our galaxy will be dark, lonely, and profoundly empty, stripped of the beautiful island universes we see today. They will be forever lost to us, their light stretched into oblivion by the ever-expanding void. The ultimate fate of the universe hinges on what dark energy turns out to be. If dark energy is a cosmological constant and the acceleration continues, our universe is headed for a big freeze, or heat death. All stars will burn out, matter will decay, and the universe will become a cold, dark, and featureless soup of dead particles, expanding forever into nothing. If dark energy is a form of quintessence that grows stronger, we could face a far more violent end, the Big Rip. The expansion would become so powerful it wouldn't just separate galaxies, but tear them apart. It would overcome gravity in solar systems, then rip apart planets, and finally, even atoms themselves in a final, cataclysmic moment. But if the tantalizing new hints of a dynamic, weakening dark energy are correct, it could point to a third, ancient possibility: the Big Crunch. If gravity eventually wins again, the expansion could slow, stop, and reverse. The universe would contract, galaxies rushing back together, heating up, until everything collapses back into a single point, perhaps to be reborn in another Big Bang. We live in a unique cosmological moment. A time when the sky is still full of galaxies we can study, yet we're just advanced enough to realize they're all slipping away. We can see the evidence of the expansion, we can measure its speed, and we can debate its cause. But we are fundamentally adrift in a cosmos whose defining trait is change. The silent, empty space between galaxies isn't just the fastest thing in the universe. It's the architect of its destiny. And it's a stark reminder that in the grand scheme of things, nothing lasts forever. We started with a paradox, something that seemed to break the ultimate speed limit. Our investigation led us through the history of astronomy, into the bizarre world of general relativity, and to the very frontier of modern cosmology. We discovered the culprit wasn't a speeding object, but the stretching of reality itself. We learned this expansion is accelerating, driven by a mysterious dark energy that makes up most of our universe. And now, we find ourselves at a scientific crossroads, questioning everything we thought we knew about that acceleration. The universe, it turns out, isn't a static backdrop for our lives. It's a dynamic, evolving, and ultimately transient place. That illusion of permanence is shattered by the simple fact that the space between things is growing. This silent, relentless expansion is carrying entire galaxies away from us faster than light, erasing them from our future and shaping the fate of the cosmos. We are privileged to live in a time when we can still see these distant worlds, even as they are slipping through our fingers. The greatest secret of all may be that we are living on a tiny island of stability in an ocean of cosmic change, witnessing a universe that is constantly and silently outrunning itself.